My name is Pratik Patel. I currently work at Azul Systems, but Java champion. Also help run the Atlanta Java user group, which is one of the largest jugs in the world. So obviously I'm based out of Atlanta in the southeast US. Does anyone not know where Atlanta is, out of curiosity? Okay, it's in the southeast US, basically. It's, let's say, halfway between Washington, D.C. and Miami on the East Coast. So there you go. Okay. And just to give you some context for this specific session and my experience with architecture and cloud, I was an enterprise architect at AT&T for a long time. And then I led the Java and cloud developer relations team at IBM, where I worked with a lot of different customers to make them successful on the cloud. And that was interesting. How many people know IBM has a cloud? I'm just joking. Don't make sure that doesn't get recorded, by the way. I don't want to get in trouble. And currently, I lead the developer advocate team at Azul Systems, which makes a Java virtual machine. And I spend a lot of time, again, with customers, helping them be successful running our JVMs on the cloud and on-prem also, right, and servers, et cetera. So, all right. And speaking of Azul, we make what we think is the best JVM in the galaxy. We have a booth here, so stop by and pick up one of these fancy shirts. And we also have these cool hats, so stop by and pick up some swag if you get a chance. And of course, talk to us about Java virtual machines. I'm not going to spend much time on this because I want to get to the content. But we have open JDK builds which are free called Zulu. It's essentially an alternative to Temurin, or what's it called now? Temurin, Adopt OpenJDK or Temurin. And of course, Oracle. And we have a premium product called Platform Prime, which is good for running in high performance environments, whether it's trading or running Apache Kafka, et cetera, et cetera. And we say with the Prime product, you get 20% performance gains out of the box compared with OpenJDK. Okay. So of course, it's a JDK, so you don't have to make any code changes. You basically drop in the JDK, you get more stability, better throughput, and of course, cloud is not cheap. So you save a lot of money by running less instances of cloud. So for example, if you're running 100 instances of Kafka with Prime, you can run 75 or even 70 instances, so you can trim it down by almost a third in terms of cloud infrastructure. Right? And we also sponsor this website called Fujay.io. How many people have heard of Fujay, out of curiosity? Okay, one person. Okay, anyways, Fujay is where a lot of folks publish content. You can also publish content, but there are loads of other folks, lots of other vendors, but it's essentially a community-run site, third-party, more or less, even though we administer it. Okay. All right. So what we're going to do today is talk about cloud architecture, and specifically around enterprise cloud patterns. And because this is after lunch, and because it's a 3-hour session, it will be interactive. So if you don't ask any questions, we'll be done in like 30 minutes, and then you can go take a nap. But what I hope you will do is, we have a whiteboard up here. As we go and explore some of these different things, please ask questions, comments, etc. And I will pick some volunteers to come up and help me kind of sketch out what these different architecture patterns look like. Okay? That sound good? Everyone's still in food coma after lunch? Okay. Okay. That's fine. We'll, that's why it's nice and cold in here, to keep you alert and awake, right? So, and Mark said that we'll have a coffee break at about 2:45 or so. So we'll take a short break at 2:45, and then we'll come back, okay? All right. So let's get started. We are going to be focusing around data management on the cloud for this specific session. Now, how many people were here in November and saw the first part of this, which I gave back then? Anybody in that session in November? Wow, okay. So the first part of this, which I gave here at Devox in November, was around migration and design patterns, specifically for going from monoliths to microservice, cloud-style architectures. If we have time, I have that slide deck too, so we can dive into those a bit later, again, if we have time. But there's approximately 3 to 4 hours of material here, assuming we make it a little bit interactive when we talk about things, okay? So, what I want to do, before we jump into this, I want to get an idea of what the experience level of the folks in this room are, right? Now, how many people have stuff running on production on AWS, GCP, or Azure? Okay, so that's pretty much everybody. That's good. How many people use AWS out of curiosity? Okay, so it's about half the folks. GCP? Okay, so that's about a third. Azure? Okay, and you raised your hand twice. Oh, three times.
Unfortunately, in all platforms.
Unfortunately. Okay, that's interesting. We'll talk about that in a bit, but okay, well, actually, let's address it now. Why do you say unfortunately across all three platforms?
It's hard not to utilize one cloud. When you use three clouds, eventually you need to be as much as cloud agnostic as possible.
Right.
Or else you need to manage three R&D groups.
Okay. If you don't mind telling us, which company do you work for?
Upstream.
Okay. Which vertical is that in? Is that like?
It's a cybersecurity and data management platform for vehicles.
Okay, got you. Okay.
We are installed in the virtual private clouds for our clients, so we are committed to the virtual private cloud that the client has, including GCP.
Oh, right.
AWS, the Azure.
I got you. Right. So your customers dictate which cloud you run on. Hence, you're on all three. Okay. So you don't take the lowest common denominator approach to that, do you? So what that means is a lot of people who do multi-cloud, what they end up doing is they say, well, these are the services which are similar across all three clouds. And based on whichever service on whichever cloud has certain number of features, that's what they will run, right? That's the level of sophistication they get up to. And they don't really use specialized or features which are just specific to that, like AWS or GCP. So do you do that as well?
Yep.
Right. So what gentleman in the back is saying, and what we call this specific issue, when you go multi-cloud, it's called the lowest common denominator type of architecture. So, like gentleman in the back, let's say that AWS supports these 5 features, but GCP has these extra 10 features for storage or whatever. Right? What you end up doing is you just use those 5 features that are here on AWS across all the clouds because it's the lowest common denominator. It requires the least amount of work to keep your system running in all 3, right? So anyways, we're not going to talk about that specific pattern because this is being recorded, so I'm not going to say too much. But most people have discovered that going multi-cloud and being restricted by the lowest common denominator is very problematic, right? So a lot of people have gone in the other direction where they say, well, we're not going to bother doing multi-cloud. We're just going to stick to one cloud and use all the features that are available on it because you have that lowest common denominator problem. So anyways, and as I'm going through some of these slides, if they're a little bit too elementary for you, just let me know, right? What I want to do initially is I want to set the stage for talking about basic cloud architecture type of stuff, right? This is stuff you probably already know if you are deploying to the cloud, but I think it helps to understand and at least hear somebody else describe what elasticity means, for example. That's the first topic we're going to cover today, okay? So one of the primary things that I like to talk about when we think about shifting from a monolith into the cloud, or even if you're running a monolith in the cloud, right? You're still kind of using the cloud if you're running a monolith, is that most developers who make the jump from a monolith-style architecture to a cloud-style architecture don't take into account elasticity across their entire architecture, right? So what does elasticity mean? Okay, what that essentially means is that you have to design for scalability for on-demand services. Right? When you typically run a monolith inside of your data center or on-prem or whatever, you have a certain amount of resources, and those are generally not really, really static, but it's hard to add stuff into your own data center. Whereas on the cloud, what you do is you basically write a Terraform script, and then you can scale up extra instances of whatever you're running, whether it's storage, your app servers, networking, et cetera, right? So we have to design for elasticity up front. And that's going to be the premise for all the different architecture patterns we talk about today, right? Because elasticity is not something you get for free in terms of how do you build out an architecture that can be elastic. Okay, so this is kind of the biggest problem. And of course, when we talk about elasticity in the cloud, we generally refer to horizontal scaling. So I'm going to, again, if this is a little bit too elementary, just let me know. and we'll move a bit faster through it or we'll move on to the next topic. But I do want to spend a little bit of time talking about horizontal versus vertical scaling, because I think a lot of people don't really understand what that means, right? But again, when we're thinking about cloud architectures and elasticity, every portion of your cloud architecture has to be elastic. Otherwise, what you've done is you've created a bottleneck, which is hard to work around at that point. Okay? So in terms of elasticity, these are the three big things we typically think of: compute, i.e. CPUs, network, and then of course data, right? That could include storage and other things like that. So these are the three main things that we have to think about as architects when we're trying to build out a horizontally scaled elastic architecture, right? And this is the point where I usually like to ask the question, but why do we want to do this? Okay, so I'm going to stop talking for a minute. I'm going to let you answer this question for me. Okay, so why do we want our cloud architecture to be elastic? What are the reasons we do this? Okay, anybody? Yes. What's that? Okay, what do you mean by demand? Sorry. Say again? Capacity. All right. So the gentleman in the back said capacity, and sometimes we call this scaling up, right? So that's essentially your answer. Okay. All right. What else? Sorry, say again?
Cost optimization.
Cost optimization. That's a good one. I like to make the joke on cloud optimization. I totally misspelled that, but you get the idea. One of the ironic things about cloud is that it actually can be way more expensive than running on-prem because you're not doing optimization. And part of the problem with doing optimization in the cloud is that it's not easy, right? It's how do you know how much you need? And yes, you have all this monitoring, but how do you do auto scaling up and down, right? Yes, sir.
Kind of connects to scaling up, but dealing with spikes. So, for
Okay.
example, we had ABC come to the office once, and suddenly the website got a hell of a lot more hits than it normally does. So we need to scale everything up for that short period. We didn't want to put it long term that way.
Right. So the classic example I like to use here for accommodating for spikes, not so close to the speaker, is do you have Black Friday here? Do you know what that is?
Yeah.
Okay. You do have Black Friday here, right? Okay. So I'm glad to see the English have copied all of the bad things we do in America, right? Anyways, so classic example of when you need a huge amount of capacity, if you're a retailer, is Black Friday, because now you have all these people who want to buy that 50-inch television for like 50 quid or whatever, right? It is. So yes, so there's that. What are some other reasons for having a horizontally scaled cloud-based architecture? Yep. Okay, that's a really good one. High availability. And when you say high availability, what are the different axes you think about in terms of HA? There's obviously the standard one, which is, you get a lot of, like if you're Netflix, a lot of people are watching Netflix between, I don't know, 8 and 10 p.m. or something, right? So there's that time-based thing. But what else in terms of high availability? Yeah.
It's easier for ops to manage it.
Okay.
Just for the manpower.
Okay. I'm going to put that as number 5, actually. And we'll say ops, actually, there's a growing field around something called cloud ops, right? Which some people consider SRE to be part of cloud operations also, right? Okay. And so getting back to your HA or high availability, what else do you kind of think about when you think of HA? What's that? Okay, that's actually the answer I was looking for, which is you have HA and also DR. And what do you typically do for DR? Right.
Backups.
Right. There's the obvious thing is backups. What's the other thing most people do for a disaster recovery type of scenarios?
Running multiple AZs.
Yes, multi-region, right? Okay, that's very good. You guys are on top of things today. So we'll say multi-region, if I can spell that. Okay, multi-region. Okay. So what else? Why else do we want? Yes, sir.
Latency.
What's that?
Latency.
Latency, right. This also goes into low latency. So this also kind of has a little bit of a dotted line into multi-region, right? So
You don't have elasticity probably your latency probably will be damaged.
Right. Okay. Right. So there's the multi-region part, i.e., being closer to the user, and then the other part of multi-region is as you get more usage, your response time goes up, and you want to kind of balance that out by having more scaling or capacity. Okay. Good. All right. Some other reasons? Anybody?
I actually disagree on the 6. Low latency cloud, it's not low latency. It's actually the opposite.
Okay. So you think cloud is not low latency?
For sure.
Okay.
So if you have your own data center, usually you have better latency than almost any cloud, even the one that is close to you.
Okay. So
6, I think everything is right.
okay. All right. That's actually a really good point. We'll touch on that a little bit. But what the gentleman said is that you generally get lower latency when you're running your own servers, right? And there is some truth in that because what these cloud providers do is they slice the CPU cycles so thin. So you're getting a V core, not a real core. And so they take a real core and they slice so that it's this small. And that's why it takes 30 damn minutes to run your CI build on the cloud, for example, right? So so that's a good point. We'll talk a little bit more about that in detail. So anybody else? Load balancing. Yeah, that kind of goes into that fits into the high availability category. So yeah, there's definitely load balancing. You need to configure networking to do proper load balancing. And when something goes on offline, you have to have the load balancer take that resource offline, blah, blah, blah. Yep. So that's good. Yep. Okay. All right. Now this is good. So in terms of what we're going to talk about today in terms of data management, we've hit all the high points in terms of what we're going to cover. So when we talk about multi-region, we'll talk about database sharding across regions and how you would do that, or what's the overall architecture for that. We're going to start talking about capacity and scaling in just a second. We won't have time to go into cost optimization. This is not something I specialize in, but I know people who do, and this is... again, hopefully this isn't being recorded or they can cut this out. If you want to make a shitload of money right now, what you do is you become a consultant for cost optimization on the cloud. And you can literally charge like £300 or £500 an hour nowadays doing that, believe it or not. So, well, you would believe it. We'll talk a little bit about surging. We'll get into some cloud ops and we'll talk about low latency as well. Okay?
I'm an AWS solution architect. Can you find some clients for me?
Well, but do you do specifically cloud cost optimization? Like, can you go into somebody's place and say, this is how you should re-architect your application or your cloud operations to bring your cloud bill down by 25% or something, right? So if you specialize in something that narrow...
We usually specialize on all 5 pillars: security, operability, and I don't know, back at my firm, I do cost optimization, like the S3 policy lifecycle and
Right.
DS scaling. I mean, I don't know, I don't have I don't know how to say it. How can I prove to a potential client? But,
Right.
I know I specialize in cost optimization. It's very granular.
Okay.
I mean, you usually specialize in cost optimization if you're a cloud architect. You say, okay, I can make your application architect for security,
Right.
maintainability, operability, and cost optimization.
Right.
Now there's a subcategory just for cost optimization.
Right. Yeah, that's right. It's cost optimization is a new category around it. Yeah.
It's a big mind.
Because as you were saying, there's already a lot of complexity or a lot of stuff you have to know about cloud to be successful, and that's as a consultant on the cloud, that's what you do. And what's happening now is that as people move to the cloud and they look at their AWS bill, they go, "Oh my God, I'm spending way too much money on this. How can I spend less money?" Right? And then the argument comes up, well, we used to have our own servers and it was a fixed cost and this is how much we paid, and now it's like 25 or 50% of running our own like on-prem or data center or something. So, all right. Is that me? Thank you. Nobody mentioned time to market, right? So we talked about like all the technical type of things, but we didn't look at we talked about cost already, but we didn't really talk much about the ability to be agile or adaptable to whatever your application needs. And nobody mentioned the time to market, right? Because normally the idea is that when you deploy to the cloud and you have like a CI pipeline built and stuff like that, you can actually get features out faster, right? So anyways, it's interesting that it's not surprising because I'm in a room full of engineers and nerds, so that we like the technical things and not so much the business side. So, all right, so let's talk a little bit about data in the app tier in terms of different horizontal versus vertical scaling. Right, so one thing that we'll spend quite a bit of time on is actually building a stateless style architecture for better horizontal scaling in the cloud. So we're going to dive deeper into that, so I don't want to go too much into detail on that specific thing right now. But of course, in today's world, we produce so much data. What do you do with that data? Do you store it for like a month or a week, store it for a few hours, or do you store it forever, right? There are a lot of people who feel that if you're collecting data, you should pretty much store it forever, right? Because storage is relatively inexpensive. So a question for the audience is, how long do you store data that you collect from your users or from your app or anything like that? Let's hear some responses. Yes, in the back. Okay. So, okay. So the gentleman in the back said our data retention policy is essentially dictated to us by compliance. Okay, that makes sense. And what? Just give us an idea of what it might be for.
As low as a week and as high as a year or two.
Okay.
It depends on what.
Okay, yeah, that makes sense. Okay. Anybody else? Yeah, right there.
3 months.
3 months? Okay.
Could be 7 years, up to 7 years.
7 years. Which industry do you work in?
Banking, for example.
Okay, right. I figured. Yeah.
I think it's important to define anything that doesn't, I mean, it's really dependent on the use case. For some it will be 7 years, and for some it will be very low. You have to have something set up.
Okay, right. So gentlemen, actually, you have, what was your name? Ron. So Ron actually has a really good point. It is, like some other people said, it's very much dependent on your app and dependent on regulatory types of things also, right? Okay. So we're not going to talk too much about like long-term storage of data. We're going to be more interested in how do you just work with data when you're building an app and you need to do stuff with it, okay? So let's talk about horizontal versus vertical scaling for a few minutes, right? So a lot of people don't really consider vertical scaling to be an adequate strategy for scaling up. But essentially, vertical scaling is when you add CPU and memory to an already existing instance, as opposed to horizontal scaling, where you add servers, and that's how you add more horsepower and memory to your application. And one of the things that I spent a little bit of time on when, for example, when I was at IBM working with a customer, is they were fixated on doing Kubernetes auto-scaling up and down. Right? And what we eventually figured out was that was not necessarily the best strategy for them. What we advised them to do is, and we helped them do it, was to actually do vertical scaling across the 10 or whatever so nodes they were running for this specific application. So that's one thing as an architect you need to think about. When does it make more sense to do just vertical scaling versus horizontal scaling? Because there is overhead with doing horizontal scaling as well as vertical scaling, right? And when we think about vertical scaling, CPU, memory, and network. Okay, so let's do this real quick. Let's think about what the cost of scaling those two different types of things up is. All right, so I'm going to try to draw this out for you, even though I already have the diagram, so that you can kind of follow along with what's going on here. Okay, so when we think of vertical versus horizontal scaling, how does that look on a graph? Okay, so if we say that this is, can you read that? Is that the right color? Nope, of course you can't even see it. Okay, there we go. Let me switch the color up. This is not the right color. Bear with me a second. We'll do white. Okay. Okay, there you go. So let's look at vertical versus horizontal scaling. Okay, and my handwriting is very bad because I use a computer, have been using a computer for 30 years and never using this thing. So this will be fun. All right, so when we think about vertical scaling, again, vertical scaling is adding CPU and memory. But let's just focus on CPU for the time being. Right? What does a typical vertical scaling topology look like? Right? So when we, on this axis, we'll say capacity. And on this axis, we will say that this is essentially like response time, right? Or latency or whatever, okay? So when we think in terms of vertical scaling, again, when we add a CPU to something, what we get is we get fairly linear scaling up until we hit an inflection point where basically our cost per request or whatever starts going up instead of staying flat. And the reason for this is when we think of typical CPU or just compute architecture in general, we reach a point where we max out the CPU and there's too much. Basically, a lot of times we've just maxed out the memory bandwidth between the CPU and the memory. So instead of being completely linear as we add more CPU and RAM to a machine, we hit an inflection point where it becomes much more expensive to keep adding CPU and keep adding memory because it just the overhead of the CPU and memory architecture and stuff like that, right? So now when we think of horizontal scaling, again, that's by adding servers, extra servers, rather than adding more CPU and memory. What happens is we get a little bit of a penalty up front, right? So it's like this initially, and then this line basically at basically some optimization point, this line becomes linear, more or less, okay? So when we think about horizontal versus vertical scaling, this is the graph that I like to show people because it gives you an idea of what's actually happening with this type of architecture, okay? Or these two different types of scenarios. So let's think about just the vertical scaling part and why that makes sense or why that doesn't make sense after a certain point. So let me just get a blank sheet up here. And what I'm going to do is I'm going to duplicate this a couple of times so I can just not do that. Right. So when we think of the number of CPUs that we put into a machine, so let's say, and CPUs typically come in pairs, right? Or not CPUs, cores, right? So we have 2 cores, 4 cores, 8, 16, 32, etc., right? And this is not exactly what I would say 100% accurate, but you'll get the idea, right? So when we think of the number of cores we have and the capacity that we're able to take, right? So we start off like here, and then again, if we draw like a kind of linear or just a flat line, we go from 2 to 4, everything is great. We go to 8 CPUs, everything is great. And then that's not exactly at the right point, but you get the idea, right? So we're basically trending along this solid line. And then when you add 16, what you see is you get this. So now we're getting like this, and then you add 32 cores, and it's like this. Right, so this is a problem when you add those extra CPUs because you need additional memory to support it, and then basically you're maximizing the backplane or the bus that is on that actual physical device. Okay, so this is where it becomes problematic when you think about this. Okay, so vertical scaling, linear to a point. Horizontal scaling, it's linear at scale, and horizontal scaling, of course, is elastic. Right, so we talked about elasticity quite a bit already, and the reason why it's elastic is because how hard is it to add extra cores to a computer? It's not easy, right? You essentially have to shut it down and then create a new VM instance with extra blah blah blah. Whereas with horizontal scaling, you basically bring something up, you reconfigure your load balancer, and boom, you have additional capacity without having to shut things down. It's basically on demand, and it's essentially seamless if you have everything done in the right way. All right, so that was a quick discussion on horizontal versus vertical scaling, just to set the base for some of the things we're going to talk about here. All right, so now let's get into some of these architecture patterns. And how many people are not Java developers in here? Okay, so what do you program in?
JavaScript.
JavaScript, okay, congratulations. I'm just joking. What about you, sir? Okay, that's fine. So you deploy to the cloud, right? I'm going to pick on you if you don't mind for a bit. Yeah, JavaScript. Okay.
Node.js specifically.
What's that? Node.js. Okay. So and you deploy onto the cloud, right? Approximately how many servers do you deploy your typical application on in the cloud?
20 to, let's say 20.
Okay, so 20 instances, right?
Yes.
And you're running Kubernetes or just?
At the moment, Elastic Beanstalk. And we're
Okay.
going through a monolith to migration.
Okay.
Which will be Kubernetes.
Okay, I got you. Now, I assume you write stuff in TypeScript as opposed to JS. Okay, that's good. And you probably work around the single-threaded event loop model by using like async await and stuff like that. Okay, all right. So, and again, I'm picking on you, so I apologize, right? But one of the things that is a little bit problematic with JavaScript is because it does use that single-threaded event loop model. And then you have to use async await and stuff like that. And JavaScript, the runtime typically has lower overhead than a JVM just because of its design and nature. But how many threads are you able to run on a single Node.js instance, you think? No, I'm sorry, threads isn't the right word. How many requests can you scale up on a single Node.js instance?
Oh, question. Don't know the answer.
Okay, I know the answer, but I just figured I'd ask you, okay? So one of the nice things about Node's event loop-based model is that, well, let me start with the bad. The bad thing with the event loop-based model is the way you have to program it, right? It's not like Java where you say execute this, and then execute that, and then execute that. In JavaScript or even in TypeScript, you have to say execute this, and then you have kind of a callback. And then within that callback, you have the next step. And within that callback, you have the next step. And you create this basically nasty nested callback architecture unless you're using something like async await, right? So that's the bad part. It makes programming a little bit more difficult, as you know, for complex types of things, right? So what people typically do to avoid that complexity in JavaScript is you break it down into different modules or into different functions, blah, 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 right? The good thing about Node's event loop-based architecture is that, let's say on a standard CPU, modern CPU, with a single core, you can normally support about 8 to 10,000 concurrent requests on it, right? In the Java world, again, all things being equal, you can typically support in a standard Java, idiomatic Java application, somewhere between 1,000 and 1,500. Which is, hold on, I'm getting to the punchline, so I know what you're going to say. All right, or actually, go ahead, please. What's that? Okay, that's exactly where I was going to go. So what you can do is if you use a reactive framework like Project Reactor on the JVM, you can get up to the same level of scale because essentially what you're doing is you're taking that kind of, threaded model and you're turning it into an async type of reactive model. So you can get the same kind of scale if you write on a reactive system because you're essentially, you're trading memory and semaphores for CPU scaling. Okay, yes?
Use Kotlin, use coroutine.
Or you can use Kotlin and use,
Or Go, by the way, coroutine.
yes, right. If you're using Kotlin on the JVM, you can use coroutines.
Reactor model and Kafka.
Yeah, or you can use Scala. Yeah. Yeah, no, you're absolutely right. All right? So, yes?
Project Loom.
What's that?
There is a
Oh, Project Loom. Yes. When is Loom supposed to come out?
one there.
There's actually a talk about Loom going on right now.
No, yeah, that's right. There is. I think we've all been waiting for Project Loom for like the last 5 years. So if you're not familiar with Project Loom, it's basically reactive style threading without having to do any of the reactive stuff, right? Or program in a reactive model, right? It's essentially a layer on top of the green threads which are in the JVM, right? Which give you reactive, almost like a reactive style of stuff underneath without you having to actually code in a reactive style. Because that's the problem with using akka or using coroutines or using Spring's Project Reactor is you have to rewrite the code in that async model, which, what's that? No, I know, but I'm just saying it's not like you're just writing straight Java anymore, right? You have to write it according to Akka's model, Actor model, or Kotlin coroutines and stuff like that. Am I wrong?
Yeah, okay, but
No, tell me if I'm wrong, please. This is great.
but so what?
Right. So what is you have this application you've already been writing for the last 5 years in standard Java, and now what are you going to do with it? Are you going to rewrite that app? Right. That's the problem.
So when you're running microservices, you're supposedly running microservice architecture, so everything is small, should ideally be small enough to be easily
Uh-huh.
writable.
Okay. That's no, I buy that. I buy that. I'm agreeing with you, right? So I'm just, making sure everyone doesn't fall asleep by introducing some friction into Yeah, yeah. No, no, I don't disagree with you at all, right? All I'm trying to say is that using any of those frameworks means you have to specifically write in that framework's model. And if you have legacy code, then you have to rewrite that code in that new model. Okay, there you go. Okay. Yeah, do you have a question? Yeah, go ahead.
It's not really the case in Kotlin though, because all you have to do is add spec keyword.
You have to add, which annotation is it? I've forgotten now.
It's not an annotation.
Oh, okay.
It's part of the language.
It's part of the language. Okay. What's that? Okay. Suspend, right? Yeah. Okay. Okay. How many people write Kotlin? Okay. Well, that's quite a bit more than I thought there would be. I didn't realize it was catching on that much. So, okay. Anyways, you get the idea. That was a little bit of a sidebar. And through this presentation, if you have something specific that you want to ask, like, well, how does this relate to a Java application or Kotlin or whatever, please feel free to ask it. If I don't know the answer, I'll ask you what you think the answer is, okay? Or somebody else in the audience thinks what the answer is. Okay, so this is, did anyone watch this TV show? It was, yeah, what's the name of this TV show? Yeah, Pied Piper, Silicon Valley. How many people watched Silicon Valley when it was out? Okay. Yeah, so when Silicon Valley first came out, I was working at a startup, and it was way too much like real life. I had to stop watching it. I'm not even joking. So, okay, so let's get back to the patterns. So one of the interesting things about all these enterprise architecture and cloud architecture patterns is that you have seen almost all of them before, but the place you see them is down here at the code level, right? For example, like decorators are, they basically translate into different types of things at the cloud level as opposed to the code level. So it's something you have to keep in mind, is that you'll probably think, oh yeah, I've actually seen something like this. And, it's just an extension. Rather than being at the code level, it's at the systems level now, okay? So there are four large categories around which most people think of these cloud patterns. And there's design and implementation, which is a talk I gave last time I was here in 1 hour. Performance and scalability patterns. We're going to talk about data management here today. And then availability and resiliency. Okay, so let's jump into the first pattern. All right, so the first one that we want to talk about is streaming data versus message queues. How many people use Kafka in here? Oh, it's less than I thought. That's about a third of the audience. How many people use or have used message queues? Right, that's pretty much everybody. Okay, so what I want to do now is I want to dive into the differences between these two types of models for building out a scalable application. All right, so one thing that I like to start off with up front is that these are not necessarily competing types of architecture. They, in fact, are complementary. Right? We'll see what that looks like in just a minute. So I'm not going to draw everything out because then we'll be here forever, and my handwriting is terrible. So, but let's think about what is the difference. Again, the question we want to ask ourselves is, what's the difference between streaming architectures versus an MQ type of architecture? So let's look at a really simple example of this, right? Say you have a thermistor, which is collecting temperature data, okay? And now you have the option nowadays of either using like SQS, or let's just keep it simple and say something like ActiveMQ, right? A messaging style architecture versus this Kafka streaming based architecture. What's the difference, or how do you think about these two different things, okay? So, so on the left, if what you're aiming to do is, if the temperature is greater than 72 Fahrenheit, turn on the air conditioning, okay? They have air conditioning in this country, don't they? I'm just joking. So I came here once in August, and I have some family here, and I was staying at their house. And this was like before the pandemic, and it was like 90 degrees or something here, and there's no air conditioning. I don't know how you people sleep in that kind of heat. But anyways, it's a rant for later. So if the temperature is greater than 72 Fahrenheit, turn on the air conditioning. So this fits better into a messaging style of architecture as opposed to streaming. If the average temperature over 10 minutes is greater than 75 degrees, then turn on the AC. Okay, do you see the subtle difference here between when you want to use one versus the other? Okay. So let's look at this in a little bit more detail. Okay? So for message queue, an example similar to the one we just had is, I want to process an order. Okay, so message style architectures are good for command-based type of processing. Okay, messages are discrete, and consumers typically act on one message. Right? We can talk about publish, subscribe, or one-to-one queues, et cetera, et cetera. But generally speaking, when we think of message queuing, this is what we look at. When we think of streaming, again, think back to our thermistor example. What we want to do is we want to aggregate messages over a time window and do something with them, right? Count them, time box them. We may want to do filterings, transformations, sums, average, count, etc. That's where streaming architectures are a better fit for the data and whatever you're trying to do around it. Okay. So, message queuing versus streaming. All right. When we think of some of the nuances of this, message queues, messages are typically deleted after processing. Whereas when we think of a streaming-based architecture based on something like Apache Kafka, or even like something like Apache Pulsar, we don't necessarily delete the messages immediately. Right? We might keep them in a Kafka, some kind of Kafka storage for a set amount of time or forever, for that matter. Okay? And because of that, in message queues, we typically don't have a history of the things that we've processed, right? The messages we processed. Whereas because for streaming architecture, we have access to the history, and then we have the ability for consumers to replay those messages to get back up to the point where we currently are in case a server goes down or you bring up a new server or whatever. Okay. On the message queue side, the message queue performs filtering, and message queues are transaction capable. On the streaming side, again, multiple consumers will typically receive all messages, right? That's obviously variable, not always the same. Okay, so these are some of the differences, right? And we gave a simple example, or a couple of simple examples, and we'll actually build on this concept of streaming versus message queuing when we talk about some of the other architectural patterns in terms of how do you build out cloud architecture. Okay. Right, so if we go into some other types, if we look at this from a slightly different way or more technical point of view, message queues are typically for doing transactions around messaging apps. We think of it almost as a RPC, or remote procedure code style message apps. We typically do pub sub with federation. That means we create separate queues to get federation, right? And typically, we have three different ways that we can do message queues. Point-to-point, i.e. queues, pub sub, or if you're using something like RabbitMQ, you have this concept of an exchange, which can do transformation and then put something onto another queue for additional processing, right? And then when we flip to the streaming side, log aggregation, right? Everyone's probably heard of that example when we think of Kafka. Fan-out based messaging apps, of course, stream processing, which we talked about a second ago, and then metrics collection is a typical use case for this. But streaming apps typically only tend to be pub sub type of architectures. Okay. Any questions so far on this, or any different experience that you had on message queue versus streaming style architectures? No. Okay. All right. So we're going to spend a fair amount of time on this specific topic, which is stateful versus stateless design. Now, how many people build stateless applications, whether it's in the cloud or just in general? Okay. So what kind of application do you have that's stateless, or how do you handle the stateless nature of the specific app that you work on?
What do you mean?
Okay, so typically when we think of an application has to have state. So for example, say you're a retailer, user logs into your application. You keep that state stored so that they don't have to log in every time, right? That's the stupidest, simplest example we can come up with. But in a stateless application, you don't have state. So like, well, what is your application that it's stateless?
Okay, I thought you referred to something different, but I also have this example.
Okay,
So, for example, some kind of transformation.
some kind of what?
Transformation.
Okay,
Just a classical example, like consume a message, do something,
okay,
transform it, and send it. Different community.
okay. There's somebody else who raised their hand for stateless? Yes.
Document extraction. So you send image of ID and you get the JSON output.
Okay. Okay, so basically some kind of document comes in, you do some processing, and boom, you send it back. You don't store the data or do multiple operations invoked by the user back to back. Okay, gotcha. Yes?
APIs like Keycloak or something like that.
Okay.
So you store your own key somewhere and then returning it within your request, and you do not keep the state
Okay.
all the time.
I got you. So the comment was you use something like Keycloak that has an authorization token, and basically that token gets passed around, so that state is not necessarily need to be kept on the server, right? So where does the data for that go? Does it actually in the token itself, or do you push that out onto like some kind of in-memory storage so that when the next request comes in, you validate the token and then you process the next step?
Actually, the best thing I've integrated with Keycloak is the security context folder, so it's keeping there.
Okay, got you. So you basically keep it like wherever you do your security authorization. Okay, all right. Anybody else? Stateless app? Yes, please.
Yeah, we just pushed to a database.
What's that?
We just pushed to a database and then thought the database.
Okay, so what you do is user comes to your website or application or whatever, right? Whether it's a real user or like another machine. And then you do some processing and then you stuff it into a database, and then you don't necessarily keep that user session alive. You basically reach into the database every time to get data out. Is that right?
Yeah.
Okay,
In one of our applications. In another one, we're very stable.
right. Okay, so those are actually all very good examples. So let's do this. Let's think about stateful versus stateless design. And what I'm going to do is I'm just going to start off with just, you already know this, but just to kind of set a base for how we would tackle stateless in a cloud architecture, how we would actually look at that and think about going stateless for something like that. So let me bring this up real quick. Okay, and what I want to do is, where's the delete on here? Clear. Okay, let's do this. All right. So experience, or is that is it the micro problem here? Right. And again, this is pretty elementary, so I'll only spend 60 seconds. Again, just to refresh your memory on what a stateful looks like. Okay. All right, so you have a user. Right, user does something, for example, does a login. It comes into, let's go ahead and add in a little bit of scalability here, right? You have a load balancer. Your load balancer will have multiple servers underneath, and that user will go to server A. And then when the next request comes in, that user will continue to go to server A. And this is what we call sticky session-based scaling up, right? Everyone's familiar with this. Uh-oh. Okay. Testing, 1, 2, 3. Oh, you turned it down in the back? That's fine. Okay, sure, no problem. All right, so everyone has done this, right? If you build a Spring Boot application, you put that at session annotation, and boom, you get state. And what happens in this specific scenario is that the state is kept where in this diagram? I know I'm standing right in front of it, but where's the state kept, right? It's kept at server A, right? What happens if What happens if this server goes down? The session is lost, right? So whatever the user was doing is basically poof, gone, right? Unless you, like the gentleman in the back said, unless you're actually on every request, unless you're storing it into a database, the session will be lost, right? And what do we call this when this server goes down and we're not doing something like that? Or how do you think about it from an architecture point of view? Yeah. What's that? Okay, not good, but so I haven't said this yet, but I'll probably say it 1,000 times. Software architecture, in software architecture, nothing is free. Or just programming, computing, development, whatever. Nothing is free. Everything is a series of trade-offs, especially when we think of software architecture, right? So the trade-off that we typically make as developers in this scenario is we say, if that server goes down, too bad. The user can just log back in and they can just redo the last 2 or 3 or 5 things that they did, right? I mean, how many people persist every step that the user does to a database? Does everyone do that for everything? I didn't think so, right? You may do a checkpoint, right? So for example, if you're like a retailer like Amazon, when you put stuff into a cart, or when the user puts stuff into a cart, you probably save that. But as the user is browsing, let's say, I don't know, they're shopping for a microphone online. You don't save every microphone that they've looked at in the database. You actually, okay, Amazon's a bad example, but you get what I'm saying, right? That's true. Thank you. Thank you for that correction. They actually do. And for some reason, Amazon, after you bought a microphone, they say, here, 10 more microphones. Would you like to buy them too? It's like, no, I just bought one. Why do I need another one, right? Anyways, it's so annoying. Someone needs to get some better artificial intelligence over there. Right, but in this case, what do? We just say, whatever. The server went down for some reason. The user will just go and redo whatever 2 or 3 steps they did. Okay, then this is a stateful style architecture. Now, when we think about a stateless architecture, right, and I'm going to ask you some questions about this in terms of how you do it, or if you're looking at doing it or you do it already, right? So what we say for stateless architecture is we again will have some kind of load balancer here in the middle, and then we'll have our servers, right? And underneath this layer, what we'll have is we'll have some kind, and this can be different things. We'll talk about that in just a second. That in my poor handwriting, that says memory. Oh, whiteboard. Yeah, gotcha. Yeah, I'll just move this out of the way. We're not going to use this for a little while, so okay. Here, can you see it now? Okay. All right. So what we do is we have some kind of memory grid underneath it. So a request comes in, the user does something, and then we store objects in this memory grid. And then when the user comes back, what just happened there? There we go. Okay. When the user comes back for their second request, it can go to any server because we're not keeping state here. There's no, why does it keep doing that? All right. Sorry about that. Let me try to, I could just draw it up there if this doesn't work, but. Okay, there we go. All right, I'll try not to screw that up now. Okay, so what we can do is we can send that request to any server because we're not keeping no state in this tier. So we can send requests to any server, and then what it will do is it will reach into this in-memory data grid, and it will set the object wherever it needs to go. And basically, it goes and pulls it out. Now, what can this in-memory grid look like, or what can it be? Right? We'll talk about that in just a second here. Okay. All right. So that's what I just drew. Right. A little bit nicer though. And so we call this short-term state storage. Okay. It could wherever you want to put the data. Okay. And then of course we have long-term state storage, which is just a typical database. Right. So if we look at these two diagrams, very similar, except for that short-term storage that we add in and the way that we think about the data, right? So if we go back to my incorrect Amazon example, the user puts something into their cart, we push that all the way down into long-term storage, i.e. into a database, but while they're just browsing something, we don't necessarily store that, we just put that into short-term storage so that if that, you know, if we need it, it's there, but we don't necessarily keep it when they come back. Yeah, what's your question or a comment?
Between short-term and long-term, like we use Redis. Is that which is supposed to be in-memory database, but it is a database.
Right.
I'm asking myself if the difference is that big, because eventually, and you know, you said about Amazon. Amazon probably, when you do that, you serve it on the local storage.
Right.
That the short, I mean, it's latency issue. Like, I think it's the same, but the problem is how far it is from your application.
Okay, that's actually a really good point. Let me ask you a follow-up question though. How long do you keep stuff in the Redis data store?
Retention is
Forever.
3 months. A long time.
Okay, so you're basically
Yeah, just evolving. I mean, things are evolving from backing of storage perspective. It's not volatile. That's
okay, right. It's not temporary storage and it's not volatile. Okay, so you're basically using Redis as a database. Do you ever flush the Redis data to like a standard SQL database or anything like that?
because it has its own usage.
Okay, not really. So you're basically using Redis as a database.
It's fast. It's in memory.
Right. Okay. So, okay. Right. So what the folks there are saying is that they basically they don't have this two-tiered architecture. Your long-term storage is your short-term storage, basically. They're combined into one, right? Now, is your application stateless then? Your app tier, is your middle app tier stateless? So you don't keep a session object in the app tier. Basically this. Let me,
Often you start seeing differences when you think about disaster recovery, multi-regions, do you replicate everything across regions?
right,
I mean, it becomes expensive, right?
right,
So even though it's the same backing stores, the boundaries sometimes are still different.
right.
Logically.
Yeah, go ahead. I'll come back to what you just said in a second, but go ahead.
Also,
No, go ahead, go ahead.
long term, the way we approach it is it's actually our data link, our get files, actually, or CQRS today.
Right,
But that's the way we look at it. We look at Redis as our state storage. So we still have the latency of request, but it's relatively low latency.
right.
And the long term, really long term, and the big data, you might call it, that you want to retain more than just a state, is the data.
Okay, I got you, right? So the gentleman up here actually brought up a really good point, right? You remember what I said a few minutes ago. Software architecture is what? It's a series of trade-offs. So what you're doing is you're trading off money for faster latency and having a middle tier that can be stateless. Because a Redis data store is how much more expensive than a SQL database in the cloud? It's an order of magnitude more expensive, right? So if you say that your database tier, if you're running, let's say, just standard Postgres in the cloud, you might pay for a very large Postgres instance with like 4 or 8 servers, you might pay $1,000 a month. But the same amount of quote unquote capacity for a Redis data store is $10,000 a month, right? So again, it's a series of trade-offs. I think that's a great architecture, by the way. I'm not giving you a hard time, right? But you probably have requirements for like low latency. And the benefit you get by keeping everything in an in-memory Redis store is that it's super fast and your middle app tier can be 100% stateless. So what you've actually done is you've traded off cost or money for having actually a simpler architecture design in that way. Because if we look at this diagram, right, you no longer have that thing at the bottom. So you don't have to worry about taking your short-term data store and flushing it down into your long-term data store. You just say, we're just going to keep everything in in-memory storage.
100% correct. In order to have under 5 milliseconds cybersecurity detection, that's one of the requirements.
Right, and that's one of the benefits you get and one of the requirements you have. So, yep. Yes, sir.
I don't know if it's this slide, but can we discuss a different that's in my mind? So again, without the in-memory database. So I use the Apache Ignite.
Ignite, yep. Ignite's great, yeah.
I want to understand when do I choose to have Apache Ignite and have a cache that is distributed along our nodes, and when to use Redis, which is third-party software.
Okay.
Because basically, I make call to a database that keeps data in RAM. When do I choose to use Redis, and when can Apache Ignite, which is already in my RAM to the nodes I use to compute?
Right. Okay.
Discuss in this presentation.
Yeah, absolutely. So the question or comment was, when is it good to use an in-memory data grid like Redis versus using something like Apache Ignite? Okay, I have some slides on that a bit later, I think. Okay, so if we didn't get to it towards the end, we can have a discussion about that. Okay, Ignite is actually a great framework. Okay, So let's talk about state and elasticity a little bit, because we've already kind of fleshed out, like, and with the great example that some folks gave, like what are the key differences, and what are the trade-offs we're making here? Okay, but let's talk about this in terms of scalability, and I want to make sure that you understand we're not talking about storing anything on the client, because that's actually a way to write a stateful architecture. Stateless architecture is, instead of storing it on the server side, you just keep throwing stuff into local storage in the user's web browser, for example, right? But what's the problem with doing that? What's the problem with, instead of keeping something in, you want to create a stateless middle tier architecture, and you're like, nah, you know what? I don't want to put it into Redis. Maybe let's put it onto the user's browser in local storage or something. Yeah, go ahead.
Using a different browser.
If he logs in from a different computer, then you will see something.
Right. It's exactly what he said. What if you use a different web browser, right? Or what if you go incognito or whatever? What are the other problems? Yes.
Security, like a joke, because you can't run it.
Okay, we have a winner right here, right? It's basically, now you're storing stuff on the user's browser. If any of that data is sensitive, or even if it's not, well, it's on the user's browser. You have no control over the security of that browser, right? So that's kind of the biggest problem. There's also a problem with latency and speed and stuff like that. So anyways, we're not going to talk about storing stuff on the client. All right, so just kind of taking a step back here. There are two types of state that I like to think of, right? There's internal state, which is we keep something within the app instance, i.e. you're using Spring Boot at session, you have internal state. External state is like what the gentleman in the back mentioned, where they have this Redis data grid, memory data grid, and so the app state is kept externally from the app tier itself, i.e. your app server or your Spring Boot or whatever you run. Okay. Actually, I didn't ask this already. I should have. How many people write stuff in Spring Boot? Okay. Okay, I have to know. Then what do you guys write in? You use KTOR, or do you use KTOR? Okay, so you use something similar to Spring Boot. If you're not familiar with KTOR, and I'm going to grossly simplify this, so don't get mad at me. It's like Spring Boot for Kotlin. Is that?
Well, exactly.
It's point for dependency injection.
What's that? Oh, right. Uses Koi instead of.
It doesn't come with dependency injection, so we still
Right, so you have to add in dependency injection. But it's basically like an app framework, similar to Spring Boot. How many people still run? What's that?
less annotation.
Less annotation hell. Yeah, I got you. It probably starts up a lot faster than Spring Boot too. Don't tell the Spring people I said that. Anybody still use Java EE? Jakarta EE? Anybody? No. Okay. That's interesting. It feels like so I'm from the U.S. obviously. When I go speak at Jugs there, like almost everybody is Spring Boot. There are very, very few people still using EE. But when you go to Europe and go speak at a conference there, like I would say there's still maybe a quarter of people are still running EE over there. It's kind of, what's that? I'm sorry, I didn't hear you. Say again.
If it's mostly banks.
Oh, asked if it's mostly, no, it's not. It's like across the board, like different industries. So, and I love making a joke there. It's like, 2004 call, they want their app server back. So, anyways. All right. So we talked about this already. Again, quick recap. If your app instance goes down when you're using internal state, you basically lose whatever's there because it's just kept in that specific app server's instance. And we do something called stickiness to route users to that specific app so we get that session app back, right? So the more interesting part is the external state. If an app instance goes down and you're running a stateless app tier, you don't lose any data, right? State is not lost because it's external, right? You're keeping it somewhere else. Now, the trade-off here is that it's not in the app instances, i.e. your Spring Boot server's memory. So what you have to do is you have to reach across the wire and you have to go and get that information, right? And now I'm going to ask you a question, or you guys a question. What kind of latency do you see when you have to reach over to Redis and grab state out of there, or any data you have to? 1 millisecond.
1-2 milliseconds, but yeah, we have others.
Okay, so one.
Just for reading. We have other stuff that we do afterwards, which is the actual processing, but just
Yeah, just pulling the data in. Yeah.
just the I/O is about 1 millisecond.
Okay, that's not bad, right?
Do you align them with the same machine or like a cross machine?
Yeah, he's asking like you have your app tier. Where's your Redis tier? Like, is it in the same? It's what?
It's in different machines, but it's in the same network.
Right, right. It's in the same virtual network that you create. Right. Okay. Right. And generally speaking, networking in the cloud is very very fast because they use 10 gig E backplanes and stuff like that. Right. So that's interesting. How long do you think it takes to retrieve a object from memory, and i.e. like a session object? How long does it take to retrieve a session object in Java runtime? What's that? Nanoseconds actually. So it's two. So your 1 millisecond is 2 orders of magnitude slower, obviously. Where if you're using Spring Boot and you have a session object kept in memory, the memory retrieval for that session object is in the nanosecond time frame. So you go from nano, to micro, whatever, right? It's basically an order or 2 magnitude slower. But it's a trade-off that you make, and it looks like it works for you because you have. You have that SLA of 5 milliseconds or whatever, right? So it works. It's great. You get lots of extra benefits. So, anyways, that's the trade-off that those folks are making. All right. So, again, when we have external state, we generally have better availability and reliability. If an app instance goes down, you're not losing the state. You also get better consistency, and of course, you get more scalability with external state as opposed to internal state. Okay. Now, let's look at this a little bit more holistically and think about external state options, right? So you can use a SQL database to do this, actually. You don't have to use Redis, okay? But let's just think about, like, what are the trade-offs between these two mechanisms, right? So we already talked about cost. A Postgres database to use as an external state store will be about 10 times cheaper than using Memcached or Redis, okay? About 10 times. But a SQL database is durable over time. The second bullet is arguable, whether it's simpler or not, right? We'll argue about that, or we'll discuss it in a minute. Obviously, going to a SQL database to either do reads or writes is slower. And what you're doing is you have complexity in the app and the database. Okay, so if we go to a memory data store, maybe not as durable, right? Depending on how much space you have and whether you expire objects off of it and stuff like that, right? But we heard the example that these folks keep 3 months worth of data in their in-memory data grid, i.e. Redis, right? You can possibly have a more complex architecture if you're doing this, right? Depends on what you do, exactly what your app looks like, but definitely a in-memory data grid is more scalable. It gets you better performance, and of course, it's more expensive. Okay. All right, and there's a blank slide there for some reason. Okay, so any other questions or thoughts around stateless architecture? We talked about all the trade-offs that you have to make, right? Cost versus speed, cost versus scalability. Yes, go ahead.
The cost is not so straightforward, I think, Redis and memory, because you can still get to very high CPU usage if you use multiple threads. So while you're waiting for data for Redis in one thread, another thread is doing CPU work and using it. So how do you calculate the cost then?
Okay, so let me make sure I understand your question. You said that there is an extra CPU cost because of.
I mean that while you're waiting for Redis to retrieve data, other threads are doing maybe more CPU because they have some available. So
Gotcha.
it's not really twofold. How do you say? Tenfold?
Well, 10 times more expensive.
Yeah.
Right. So you think it's more or less than 10 times? Less. Okay. And your reasoning why it's less is because your CPU is not waiting for data retrieval or whatever.
If you use enough threads and it works with enough CPU cores, you can get to high CPU utilization.
Okay.
Even if you have Redis.
Okay.
So it's still busy.
Okay. I understand what you're saying now. So what you're saying is that because you're keeping the data in an in-memory data grid, what you're getting, the additional benefit you get from that is that you can push your app tier CPU harder because you basically have faster access to data.
No, there's still.
Oh, okay.
Still a cost, but I think it's less than threefold.
Okay. So instead of being 10x, it might be 5x more expensive. Okay, that's fair enough. So I don't know how much Redis cost on Amazon, but it's not cheap. Last time I looked, so that's a good point. All right, so let's do a quick time check here. Hey, can you? Hey, you in the back on the phone? I'm sorry, I don't know your name. Yeah, have they brought the coffee out yet? Can you see? Should be right there. No, right. It should be right outside the room. Okay, so let's do this. Since we're at a good stopping point, let's take a 15-minute break. All right, so let's get into caching and talk about this for a bit. We're talking about a couple of different cache strategies, and as you'll see, a lot of the stuff that we're going to talk about from here on out, everything kind of builds on top of each other or is kind of interrelated to, right? So this is one of the interesting things about software architecture is that none of these patterns or the way that we think about architecture is disconnected from other things. Everything is kind of connected, and at the end of this session, we want to think holistically, like about your entire architecture. Like, we can say, okay, let's do stateless type of architecture, which we just talked about, or app tier statelessness. But then, like, what about retrieving data and having materialized views to get faster data out of a database or Redis or whatever, right? So there's a lot of interconnection between these things. But anyways, let's get going and start talking about caching. And as you probably know, the primary use for caching is performance, right? And also lower latency. But I'm not going to draw this out. We just talked about this diagram a bit. But this is the typical way a cache works, right? You have an app. Is something in the cache? No. Go and get it from the database, store it into the cache, and then return the data, right? If it is in the cache right here, then we just go retrieve it from the cache. It's relatively straightforward, right? Everyone typically understands caching, but let's talk about some of the nuances of this, right? So, and unfortunately, I've already gotten to the punchline, so I'll just scroll back. What's the hardest thing in computer science? Everybody. Naming things. And what? That's right. Naming, and the second hardest thing is tuning a cache, or when to evict a cache, right? So
I think the original quote is naming and cache validation.
there you go, cache and validation, exactly. Original quote, exactly. There you go. So, anyways, right. So why do we use a cache? It should be a lot faster than querying a regular database. But the trade-off here is that a cache is typically smaller than a database, unless, of course, like the folks at Upstream who just keep everything in Redis, which in a lot of ways can work as a cache also. Right, but one thing to note is that caching typically uses both strategies, right? So let's talk about what that actually means, right? But, of course, caching is app dependent. So there are two typical types of caches. There's what we call an active cache, which is write through, which basically means that everything is just kept in the cache, right? So it's what we call an active cache, whereas a cache aside is what we had in this diagram right here, right? So because the size of the cache is typically smaller than our entire database, what we have to do is we have to somehow load that cache, and then, all right, let me get back to the slide, and then when a request comes in, what we do is we say, okay, go get the data and then stuff it into the cache because we're probably going to use it since we just retrieved it, right? That's called lazy caching as opposed to active caching, which is also commonly referred to as write through. Okay. And of course, the benefits of a cache, read performance. Another additional benefit is that you can substantially reduce the load on your database, and that gives you better overall app performance. And the way that we work with, and we've already made a joke about this, cache invalidation and data consistency. But when we have a cache miss, we load that from the data store, and we have to figure out when we want to evict things from a cache. When do we not need this data anymore, right? And a typical strategy around this is we'll say, okay, we put something in the cache, and we'll keep it in the cache for 10 minutes or something like that, right? So this is something that you have to find out typically through trial and error, unfortunately, right? And there are other ways to do this, of course. You can use different kinds of metrics that your application dashboard has, or maybe you just know that this from your business logic or your whatever you're trying to implement, that the cache will be needed, or this data in the cache will be needed for X amount of time. Okay, now this leads to we'll talk a little bit more about data eviction, but one of the things that is also difficult to figure out is how do we prime a cache? Okay, so what that means is you, for some reason, you've shut down your whole application, right? Maybe you're doing maintenance, maybe you're releasing a new version of your application and you need to do a shutdown of your app. Now, how do you go and load the cache up, right? Or what we typically think of this as how do we do a little bit of optimization for getting the cache loaded up with stuff. So if you're using like the cache aside strategy, which is lazy caching. So whenever you need the data, then you go put it into the cache. So your cache builds up over time as data is needed. But what happens in that scenario, right? What's the problem with when you bring up your system, right? Say you do a complete shutdown. You bring the system up, there's nothing in the cache. So what's the problem with starting with a lazy caching strategy? Yes.
Two problems. Your first is your latency is going to increase.
Yes.
Second is the database is going to get strained.
Right. Absolutely right. So that is exactly it. The comment is when you bring your app up and there's nothing in the cache, you're going to have a lot higher latency because there's nothing in the cache, right? And the second problem is now you're just hitting your database a lot, right? Now your cache is being populated, but it takes time. So one way to work around that is we do something called priming the cache. That means your app comes up, you run some kind of external process that goes and pushes data into the cache so that you don't have to rely 100% on lazy cache loading. Okay. Now, this in and of itself is also an art form, but I typically find that it's not as hard as it sounds. Because if you think about your application, what are some of the things which you definitely know your app is going to need when it starts up? What are some things that, so if we use our stupid online retailer example, right? What you might push into the cache immediately on startup is your entire item catalog or your entire product catalog because you know that's going to be used. You're not going to load it up with user data because as users come in, then you'll load user data into the cache or whatever. But you know for certain that for your, again, using an online web shop type of thing, you know that people are going to be looking at items. So let's just load them all into the cache. So a lot of it is business dependent or whatever you're trying to do. Okay. All right. So I don't want to go too much more into cache on this or too much more into caching because this alone could be like an hour or two or three talk. Yes, go ahead.
What about using, well, I've noticed sometimes for this scenario, there's not just a hot tier and a cold tier. Sometimes there's like a warm tier. So it doesn't hit the cold storage, but it does use a cache for the really hot data. And then when the app starts up again, then it can load it from the warm tier instead of straight from the.
Okay. Yeah, so the comment is that some people use a multi-tiered caching strategy as opposed to just having a cache. You have a hot cache, like you were saying. You have something like that resembles a warm cache, and then your cold tier is basically your database, right? Or are you thinking something different along those lines? Right. Okay, so let me ask you a question. Do you guys do this kind of caching, first of all? No. Okay. Or, it is complicated, but what do you think about when you say warm tier or warm caching as opposed to hot caching? Like what's an example of that, or what are you thinking about when you think a warm versus a hot cache?
I think, well, if you look for example at ad hoc queries running for example tree on top of the object storage.
Okay.
Then object storage would be I think the cold tier.
Right.
Warm would be SSD
Okay, I see. Okay, right. So the comment is, if you do like basically three tiers of data storage, right? Your hot tier is memory, something like Redis. Your warm tier would be something that's on a fast subsystem like SSDs, but not as expensive as RAM, right? And then your cold tier is basically file storage, right, or object store, right? So I'm trying to think if I've ever worked with anybody or done this myself where there's an intermediary tier. And unfortunately, I don't think I've ever personally worked in that type of multi-tier cache before. So, have you done that?
In payment system, so it's not really at cache level, it's more at database level, storage level, where we have a partition database and we move partition to colder tiers.
You move it into what?
So we have hot tiers, we have cold tiers, and we don't need all the indexes when we have all data, all page. So maybe a few record queries on these payments. We don't need all the indexes that we need for real-time payment processing.
Okay. And so you move the basically the indexes or essentially a B tree type of thing.
Partitions
Okay.
from one tier to another tier, which is slower but less frequently used.
Okay, I see. So that's actually almost a completely different architecture than hot, warm, and cold, because what you're doing is you're doing what sounds like federation or almost sharding, right? So you keep stuff that's not accessed that often over here, right? Is that
It's part of the ILM information lifecycle management, where we use kind of expiry data, the data partition and so on. And when it gets older, it's moved to slower storages.
okay? And you manage that architecture by yourself?
That was yes, that was a solution implemented like 10 years ago on Oracle.
Okay, on Oracle. Okay, interesting. So do you use just 1 second? So do you use coherence, Oracle coherence in there anywhere?
No,
Just the database server.
standard partition, console, and detaching partitions.
Okay, so if you're not familiar, Oracle coherence is an in-memory data grid, similar-ish to what are some of the other products in the coherence space? I know Terracotta Tech used to have one. Who else? Anyone know what's similar to coherence? It's basically an in-memory data grid, similar to Hazelcast. Who else makes something that's what's the Apache one? There was an Apache in-memory data grid too, right? What's that? Not Ignite. I'm thinking of something else. Yeah, you're right. It is an in-memory data grid. I'm thinking of GridGain also. So I think GridGain is built on Ignite. But anyways, okay. Yes, you had a question or comment?
And just in comment to the previous like nearly the same architecture we had we use Redis as a cache.
You use Redis as a cache.
Caches, yes, and we have a hot caches like a neo caches or it's like a taxation service and for the some reference data which is like a very common for all the like for example list of taxes or list of the countries that apply these taxes. These are all kept on in a hot cache. There's lots of other data which is like specific to the like user entries. We keep in a Redis cache and we use the like a client server model of Redis cache.
Okay.
And it is like as well as distributed. We were deciding for the Hazel for this and yeah, there's an on-premise, so we're choosing a Redis, but this is the example like that we use the client server cache and whenever the application will get down, all this data still is there and only the hot cache that is like very specific data there will be lost.
Okay, I got you. So her comment was basically you use a multi-tiered cache. You have like a hot cache at the top, which is Redis, and then you have another tier of cache below that, which is also in Redis or is in something else?
No, neo cache is in memory.
Oh, near cache is in memory,
Yeah,
and then
Redis because we have the latency issue that we have as in like a
got you. Okay, right. So that's interesting. So their architecture is you keep stuff in memory on the app tier itself, like in process, and then that's basically your immediate cache, and then your near.
H cache or something like
Right, use something like cache to do that, right. And then that's basically in memory in the app process. And then the tier below that is like a Redis cache, which is obviously going to be larger.
Yeah, and we deal with it because like there are just like civilization programs with the latency as well. So
Right. Because of latency, you have that multi-tier to get better latency, just keeping everything in process in process memory. Interesting. How many people use cache out of curiosity? Okay, so a couple folks. What's that? Oh, just for development, not in production. Right. Everyone using Hibernate. Okay, that's. I don't know if everyone who uses Hibernate uses cache though. Yeah, you have to enable cache in Hibernate, right? It's not by default. Okay. All right. So it's good discussion. Thanks for that. I don't typically see a lot of like multi-tiered cache, but I know some apps have it. I think nowadays for the cloud, people just throw everything into that, what you were saying, like basically into a Redis cache layer or something like that. And of course, the guys at Upstream, they just use that as their database. So do you guys use a cache at all for your stuff? No? Okay. Well, I mean, you have everything in Redis already, so why do you need another cache?
We have like maps. In-memory maps.
Right. So you, like this lady at the front, you keep stuff. Right. It's basically in memory on the process itself. Right. Got you.
We have our main casting is for compute for
Right. Okay. So let's take an aside. Actually, now that you brought this up, so we're talking about caching. We're talking about keeping stuff architecturally, stuff in memory, so that you could do very fast processing of it. You don't have to reach into cache to get the data, right? Because of the 1 millisecond latency. And then you have this second layer that like a Redis, and then of course your long-term data store if you have it. And not everybody has that. Why don't you use Apache Spark to do your processing?
Smart streaming, you mean?
No, just Apache Spark, right? So what you do is you have processing that needs to be done. And, well, maybe Spark streaming, right?
Our processing, for instance, almost near real-time detection.
Right. Real-time detection.
Spark works on batches. Regular Spark will work on batches, so it's not that. So
Okay.
if I'm working on Spark streaming, which is actually micro batches, we could use that, but we are trying in our architecture to avoid monsters. And the way we see Spark, definitely Spark streaming, is a very hard to maintain monster.
Okay.
Not running
Yeah, no, it's fine. This isn't being recorded, so don't worry. I'm joking. It is being recorded. So, yeah, go ahead.
Actually, we did try to use we had an adventure with the Apache Spark streaming once, and we wanted to do is just to write ORC files to object storage.
Right.
We ended up giving that up because we found out that just writing our native writer was about seven times
Interesting.
7 times more performant. Yeah.
Okay. That's really interesting.
It's not like it was doing any processing. It was all I/O, and it still was taking
Right.
a lot of CPU.
Yeah.
For classic batch processing, Spark, I believe, is great
Right.
in most of the use cases. For streaming,
Right. It's streaming. You're probably better off using something like maybe Kafka, and maybe not even using Kafka, depending if you want to be real time. Right, you are using Kafka, right? So that's interesting. Apache Spark. Everyone knows what Spark is, right? It's basically an in-memory data processing engine that can be fully distributed across different servers, et cetera, et cetera. Now, what's interesting is that I think you guys hit on some of the not edge cases, nuances, I would say, with Apache Spark. There are some internal latencies because of I/O bottlenecks, which you mentioned, right? But there's something very specific in Spark. We were talking during the break about Azul's high-end proprietary JVM, and one of the platforms where it doesn't, Azul Prime doesn't work very well on is Apache Spark because of the way that the Spark processes are done and they're compiled at runtime. What happens is you can't do JIT-based optimizations on those because, right, the way a JIT works is you have some code, it runs. The JIT says, oh, I can inline this, or I can do call side caching on this specific sequence of, basically Java ops, low-level Java operations. But if you're compiling at runtime your Spark SQL or your Spark processor, you can't do JIT compilation and optimizations for those, right? So there's like little nuances there that you have to be careful of when you're using Spark. Don't get me wrong, I think Spark is a great platform. And there's a previous customer who I've worked with at IBM. I'm not going to say who they were, but they were thinking about using Spark to do like basically their problem was they have these 100, not 100, they have these 8,000 inputs and they need to calculate every variation between those 8,000 inputs. So those 8,000 inputs basically become billions of different paths, right? That they basically then need to query those billions of paths. And they started down the road of using Spark and they ran into some of these problems. But they started off building this as a Kubernetes cluster, right? Just writing app code. And I'm like, well, you should put this all in memory. But you know, over time, they discovered some of these things. They found some workarounds with it. So it's still a great platform for like keeping a huge amount of data that you need to either query or process using standard objects. But and a lot of Spark code is also, a lot of Spark code that you write is also in Scala, right? So that's a little bit of a hurdle. How many people use Scala, just out of curiosity here? In the past. Now use Kotlin, right? Anybody use Scala?
I'm still traumatized by that.
Okay. I'm glad you said it, because I didn't want, yeah, this is being recorded, so I didn't want to say that. But yeah, it's, I don't know. I also much prefer Kotlin to Scala, right? And of course, Java is great too, but anyways. All right, thanks for the discussion. Let's move on to materialized views and talk about this for a minute. All right, so everyone has probably heard of materialized views, but the context in which I'm going to talk about materialized views here is not necessarily in the context of SQL materialized views. They're kind of the same thing, but let's think about it again architecturally at a little bit of a higher level. Okay, so when we think of a standard view, again, if we just use a relational database, we have, it's essentially a named query that pulls data from tables. That's just a standard view, right? Everyone has done this before, right? Whether you're using Hibernate or not, right? You're writing your own queries, that's what you're getting, right? And then you have something called materialized views, which again are not just for relational databases, okay? So what does this actually mean? Right, so if we look at the thing on the left here, right, we have a standard table, right? These are t-shirt orders, okay? And then we have another thing on the right called item sold materialized view. And hopefully this helps you see what the difference is. The thing on the right, we're doing some computation, in this case aggregation, okay? But we need to have this thing on the right as a dashboard for our operations people. Right? So we don't always want to continue querying the table on the left because we'll put too much load on it. Right? Again, this session is about data management. How do we work with data in an efficient way in the cloud especially? Okay? So what we want is we want this materialized view. Now there are a number of different ways of doing this. Okay, so first, when you think of materialized views, the premise is the data is stored once and then we retrieved repeatedly. Right? So it's almost not like a cache, right, necessarily. But it's something that we know we're going to need over and over again. Yeah, we can put it into a cache, right? Maybe we can put it into Redis, whatever. But we also think of that as a materialized view, whether it's in a database or whether it's Reddit, right? We're doing some kind of aggregation or computation or something. So that's the key difference here, okay? Almost like a cache, but has its own store, right? Now, materialized views typically need some kind of trigger to populate it, right? So let's say that new orders come in. Now you need to go and update that summary materialized view. So you need to have that kind of mechanism. Again, if you're working in SQL, if you're using Oracle, it supports this down at the database level. But nowadays, again, if you wanted in something faster like Redis or some kind of memory cache, then we have to figure out how to do this. Right? So when the data store gets changed, we need the materialized view to be updated. Now, there are a couple of things that we have to be careful about when, again, just conceptually when we think about materialized views in terms of architecture. It's not good when data changes quickly or you need strong consistency. Because if you remember the previous slide, we have to have some kind of trigger that pushes stuff into a materialized view, or we have to reconstruct the materialized view or whatever. Right? So there's going to be a little bit of a lag there. right? So how sensitive is the data that you're reading out of it? Does it have to be 100% correct immediately when anything gets updated? Well, you probably can't use it in Materialized View then. But if you can tolerate a 1 or 5 or 10 millisecond lag in terms of when something gets into the system as opposed to when it needs to be read, then you're okay. Okay, so Materialized View may not work great, for example, for, oh, I don't know, like a bank account, right? But it would work fine for a order aggregator view into how many orders have been placed today. Because yeah, you care about being consistent and correct with that, but it doesn't have to be immediately consistent and correct, right? It's what, we'll talk a little bit more about this quite a bit, but it's what we refer to as eventual consistency. Right? You probably heard that term before. Okay. All right, so the reasons, aside from that read performance, that we want to consider Materialized View is it gives us the ability as developers to shape and size the data appropriately, right? We talked about aggregation and doing like some operations around that, the simple example. But a lot of times we'll have data spread out across multiple stores or across multiple tables in the same store or whatever. And we want to have really good read performance, but while we're at it, why don't we create exactly what we need or what the user needs to see or whatever we're processing, okay? So it gives us a chance to shape and size the data appropriately, and we can create these materialized views based on specific use cases. And of course, we can include calculated fields and transformations. And one thing that we need to be aware of is the materialized view should be easily recreatable. So if the materialized view goes away for any reason, or if we get a big update, we should be able to recreate it immediately. Okay, so remember I said this is not just for database. We can do this in Kafka, right? So if we look on the left, this is a KSQL. We say create a table called part average, and then we go and select stuff from a Kafka topic. Okay, and what we get is the thing on the right. So as data starts streaming into our system, the thing on the right will get updated. Right? So this is a materialized view on the data. Yes?
Because I have experience with that.
Yeah, go ahead.
I have to protest. With the Kafka example, this is a K table. Actually.
I'm sorry, K table. I'm sorry, yeah.
You're right. This is a K table. No, you're right. This is a K table. I mentioned it in the break. The biggest disadvantage I think in this thing is the way it's stored. I mean, you get data locality, it's stored in your microservice in
Right.
memory. But the problem is that it's really hard to maintain. It's on RocksDB. You can't control how big it is. And on theory, those material views are amazing because they are streaming-wise from
Right.
Kafka being recalculated all the time. In practice,
I'm sorry, say again? Right, it uses a RocksDB, which is a key value store, right. Ah, okay. So what you're saying is that it's not really queryable then, right?
no, it is queryable.
Well, I mean, in performance-wise.
The problem is it's not even performance. The problem is that you don't have control of what it actually does behind them. That's the problem. Opposed to Redis, where you put so many aggregations which are manual materialized views, this is actually automatic materialized view, which is cool.
Right.
If it wouldn't have worked well.
Okay.
My claim is according to my experience.
No, it's fine. This is good. So okay, so you're saying a custom state store might be a solution to what he's talking about.
That's exactly. Oh, custom state store. By the way, okay. For example, the problem is when you are using the K table, it's doing serialization and deserialization all the time.
Okay.
We did in the former example. We actually rewrote half of Kafka Stream's library in order to say when doing memory, don't serialize, deserialize, because this is a very high intensive CPU.
Right. It's an expensive operation.
And
Right.
we wanted to save it, in memory as objects and a lot of other stuff like that. You would have thought that custom state store is an easy way to do it, but the interface is extremely hard. They don't
Gotcha.
let you do that. Again, from experience.
Okay, so let's summarize this for everybody, especially for the recording. What are some of the problems with these materialized views in Kafka?
So I would say first and foremost,
Yeah.
they try to do it unified, so it could be flushed to disk and
Right.
in memory, but then you lose from this side and other side because you don't gain the in-memory, benefits such as don't serialize and deserialize on every
Right.
operation. Those operations happen all the time. All the time, query your state store.
Right. If I could summarize that piece, what you're trying to say is that it's an expensive thing to do in terms of CPU, memory, overhead, all those kinds of things. Okay.
The advantage, I have to say again, is that it's automatic.
Right. And it's super easy.
Yeah, it's super easy.
Right.
But it doesn't hold in production.
Okay.
Again,
No, I think that's great feedback, actually, right? So I've used these things before, but not at huge scale. Like you guys are doing this stuff where you need like really, really short response times, and you probably have lots of data and things like that, right? So, right, okay, interesting. All right, yes, go ahead.
What happens if you do an aggregation that has to look at the whole data from the past? For example, count distinct. It can't really be incremental, right? It has to look
Yes.
at everything that it has seen in the past.
Right.
Is it even possible in this?
Right. So the comment is we talked about this kind of at the beginning when we talked about streaming versus MQ architecture. One of the advantages of Kafka is that when you put stuff into a Kafka topic, you can replay that entire stream to rebuild where you are at today or now. So if let's say you keep 3 days or a week or a month's worth of stuff in your Kafka topic and something goes down over here, you can replay all those events to build up to where you are here and get the materialized view or whatever processing you need to do. And the comment is, what if that's really big? How long does it take to get from 7 days ago to today? And how much CPU, memory, etc. does it consume? Is that your point, right?
Are you saying that this is also reading the entire topic?
It doesn't have to, but if you do a replay, yes, this materialized view will read, and build everything up because it has to, right? If you think of basically Kafka is just a stream of data.
I thought that, for example, in this average is simple to do incremental.
Right?
So I was thinking that every time a change happens, it just calculates a new average for each
Yes.
area.
Right. That's right.
Is that what it does, or does it read the whole?
No. Okay. So I love this answer that I'm going to give. It depends. Because if you do a replay, yes, then it has to go through everything. But if like you already have the stream running and you say, okay, I want this view at this point in time, it'll only be from that point in time forward. But if you're doing a full replay, then yes, right? How do you reliably get the average over the last 7 days of the time of your stream if you do a replay? Well, it has to compute all the way from the beginning to where you are now. But if you say, hey, I want to see what the average is starting from now until whenever I turn it off, then yes, right there at that point in time, it will start counting from that point in time or doing the calculation from that point in time. So you can do both is what I'm getting at. So, yes. Yeah.
label things, I think it's called event sourcing.
Yeah, event sourcing. Yeah.
Sourcing now, again, very nice in theory, very complicated.
In practice. Yeah.
Really complicated.
We're going to talk about event.
It's amazing.
Yeah.
It's really hard to do it.
It's, I would agree with you. We're going to talk about event sourcing in a few minutes, so we can you can give us some of your experience with that also. All right. So if we look at this in JDBC, and this is using a JPA example, right? So if you're just doing SQL, it's actually very easy to do a materialized view against a database. Because what you do is you say at entity, right? You recognize this as JPA. But the key thing here is that this annotation right here, at immutable, right? So you're basically, again, materialized view is read only, i.e. the object that you create that represents that materialized view is immutable. Okay. So, and then of course you can have some kind of strategy. And if you're creating a materialized view, it's only read only anyways. So, okay. So, and this is what creating that looks like. And of course, this is also the important part, creating the appropriate indices for speed. All right. So we're going to take a little bit of a step back before we dive into more of the nitty-gritty stuff like the event sourcing, CQRS, and stuff like that. I want to talk about replica sets for a few minutes here. Okay. First of all, what's a replica? Everyone has probably seen this before. So if I have, I'm going to go through this rather quickly. But if you have a question, again, please feel free to ask. what is, if we just look at standard Postgres, you can create replica sets. MongoDB also supports rep. Anyone using Mongo out of curiosity? Okay, a couple folks. Okay. Mongo also has this concept of replica sets, right? And the way that this works mechanically is you have your primary Postgres database, you have your standby, and you have what's called a wall sender and a wall receiver. It's basically a streaming log of all transactions to the database. And you stream from one to the other. And what you can do in this specific type of setup with Postgres again, right? The wall is defined right here. It's a write ahead log, i.e. it's basically a full transactional log of everything that's happening, right? And what you do is your application does read and write to this thing, but it only does reads from this other. And what that thing on the right is called is it's called a replica, right? And it's only meant for reads, typically. Right, so if we think about how this works, we have a master where we write everything, and then we can have multiple read replicas on this. Okay, and again, what you have to be careful about is eventual consistency, because if you look at this, you can spot where the bottleneck here is, or the latency. Right, it's easy. Right, the latency is right here in the middle. Right, the log getting sent over the wire and then replayed over here to build up this replica. So you will have some kind of latency. Now, let me go back to this diagram. So how many people do multi-region in here out of curiosity? Okay, I'll ask you in the back. Do you do active multi-region or active standby multi-region? God damn it, only I can say it depends, okay? You're not allowed to say that. But no, I get it. So you use both active and active standby. Do you have data stores or databases which are active multi-region? Pretty okay. Which database do you use? Okay. Okay. For the folks that don't know, Aurora is basically MySQL running on AWS. Right. Go ahead. Okay. Okay, it's fair enough. Okay, I think somebody else raised their hand. Yes, go ahead.
We did a small prototype with a multi-region active with Cockroach DB.
With Cockroach DB, interesting. Cockroach is actually a great DB. So I don't like the name, but it's like, come on, guys. Yeah.
They say it survives everything.
It survives everything. I know. Okay, yeah.
Not in upstream, but in my previous workplace, we had two Hadoop clusters, Hive.
Yeah.
And they were active.
Okay.
But the problem was that the users hated it because they would sometimes it causes a scenario where one user queries, for example, cluster 1,
Right.
the other one queries cluster 2, and they get two different results, and they might be in the same team.
Right.
They really hated it, and even in disaster scenarios, it didn't really help because in order to actually help you in disaster, each cluster has to be able to handle the entire load of users. And in this case,
Right.
it couldn't. So when one cluster went down, the other one went down twice.
Yes. Yes. All right. So I'm glad I asked you guys these questions because you hit on almost all the problems with doing multi-region types of architecture for the cloud. Yeah, go ahead.
By the way, question, like, is it multi-region or multi-AZ active?
Oh, okay. So I can say this. It depends.
Well, it's a little bit different.
Right. No, you're absolutely right. All right.
It's easier to do multi-AZ active.
That's right. It's easy. The comment is it's easier to do. Sorry, you say it again.
Yeah, it's easier to do multi-AZ.
Multi-AZ active. Right. Easier to do that.
Multi-region active very hard because of the latency.
Right. And exactly right. It's very hard to do multi-region active because of the latency. Much easier to do multi-AZ active. Right. Okay. Good. Yes.
It's quite interesting. I think I saw once Samson Creator, he called it turn the DB inside out, which actually what he did is taking that stream that makes the replica and said instead of doing this as an internal thing that the user does not see in the database,
Right.
You use a repository, you just update the tables all the time. So let's take that inside mechanism and take it out for instance, as Kafka, which is
Right.
mechanism
Yep.
start, and then do again. But again, this is a concept that says Kafka in the database, everything that really nice in theory.
Yeah, hard in practice, right?
I would say not working well in fact.
Okay, not just hard, it doesn't really necessarily work well.
Go turn the database inside out. Really good.
Gotcha. Okay. Cool. So there are a couple other things. Again, we're talking about replicas. We kind of took a little bit of an aside there in terms of multi-region. But typically when I think of a replica is within like the same cluster in the same data center or whatever, right? Same region. And one of the reasons why I like this technique is because, wrong button, is that you can tune replicas for reads, which is super helpful. You can tune the master for writes, and of course, you know, we have to have some kind of way to to do this. But the reason why I like talking about this is that if you just need scale, and especially if your use case is, I need to do a lot of reads, this is so easy to do. It doesn't require a lot of thinking. You don't have to reinvent your architecture much, or or change your architecture. It's and almost everything supports replica sets, whether it's Mongo, Postgres, Oracle, etc. So it can solve a specific class of problems. And we talked earlier about like, hey, let's put a cache in, right? Caches are great, or let's put this in-memory data grid in. But what you're doing is you're changing your architecture. Now you have to code things, and there's more stuff to manage, and it's more complex. Whereas with replica sets, it's like, let's just create a replica of these databases, and we don't have to change any of our code, more or less. Right? So it's super easy to do. And this is kind of a known art because we've been doing it for years and years. Okay? So, all right. So let's get into sharding. And this is a fun topic. How many folks do database or data store or whatever sharding right now? Anybody? Okay. What's that? You did. Okay. You mind sharing your story on?
So it was with Akka.
Okay.
It was sharding within Akka. So you can basically shard on a particular entity ID, and that will be separated down into that particular node. The requests will be forwarded towards the
Okay, got it. Yep.
specific entity ID.
Right. So classic sharding, basically. So why did you say you did sharding?
I don't even join the company at this point, so the history is a little bit murky. But in short, it was very difficult to limit the amount of shards. So they represented an entity, and we
Right.
had multiple of these entities, and we couldn't kind of set a limit on the amount of shards.
I believe this was the base, wasn't it?
So we had to cap it, and we didn't want to cap it because obviously this limits our capacity too much. So
Right. Okay.
we decided not to go with it.
Right. So we're going to talk about that specific problem in a few minutes. But thanks for sharing. So anybody else do sharding here? Out of curiosity, you guys do sharding, right? What's that?
Distributed Redis.
Okay, you do distributed Redis.
Cluster. We have a Redis cluster.
Right.
That's the way it works. It's being sharded.
Oh, right. So but
Automatic, by the way.
so Redis now supports automatic sharding based on the key.
We didn't believe that also.
Okay.
Done it in, but that's the way we got
And
the cluster without.
right. So help me out here. When you do Redis sharding, you provide a key or something that it's supposed to shard on, and then it just automatically just balances. Okay. Wow.
We needed the application.
Okay, well, this section of sharding, or this section is going to be really short. Just use Redis sharding. It's the easiest thing to do. Right. All right, but let's talk about it conceptually. So you at least know what it's about, right? So sharding, I don't know why that says sharing. It's for scalability and perf. And what does this actually look? Well, okay. So again, what we're doing is we're trading complexity for performance, unless you're using Redis where it just does it for you automatically. But let's look at this. The main reason that we think of sharding is because data stores have limitations on space, compute, and network, right? So, we talked about replicas for reads. We've talked about other things like caching to get better performance and to get scale and stuff like that. Sharding is one way to do this, right? So if we look at it from a very, very simple point of view, say you have a table called user table, and then you have, again, this is just a very simple example, right? So if you don't shard, this is what you have. But when you shard, you say, okay, everything in database 1 or shard 1 is first names A through M, and everything in shard 2 is all last names N through Z. Okay? So what you do is you're splitting your database into two different databases. Now, this presents a whole host of complexities and other things like that, which we'll talk to. So, by the way, does anybody recognize these names here? See if there are any sci-fi nerds here. Come on, someone has to recognize the names here. Yes. Stargate. Thank you. You win a prize. So, Stargate SG1 specifically. So, all right. So we split data into horizontal shards, and then we balance the workload across the shards. You can probably think already what the problems are, right? So let's do this. We don't have a lot of time left, but I think this will be fun. Did he? Oh, okay, good. I was going to say Mark didn't leave me he didn't leave me an eraser. All right. So what are some of the problems that you might anticipate with sharding? What's that?
A hot shard. A hot shard. Hot shard. I mean, if there are a lot of names between A and M and a few between N and Q,
Right.
there will be a lot of data only in A and
I got you. So unbalanced shards. Okay, so that's one. That's a good one. Actually, we're going to talk about that. Unbalanced shards. What else, guys? What's that? Okay, that's a good one. But is that a problem or is that a benefit? So the comment was, what happens if one of the shards goes down, right? And only that part of the data is lost. But that is a problem. Okay, so let's say a shard goes down. It goes offline. Okay, what else? I'm sorry. Let's start here. Okay, so basically the sharding strategy can be a problem. Is that what you're saying? Right. Okay, got it. So sharding strategy, we'll talk about this a little bit too. This can be a problem, or it can add complexity, et cetera, et cetera. Okay. Yes? I'm sorry, say that again? Network partitioning. Okay, so what do you mean by that?
It's possible that you are unable to reach a particular shard at that point, so you end up creating stale data that's inconsistent with the actual, what do you call it, the first shard that you created. So maybe due to like stone network or something, so you cannot actually like contact the first shard that you are, and you end up like into the different shards. So you can have like inconsistent data.
Okay, got you. So that's actually a good point. You can get inconsistency with data between shards, right? So we need to talk about what do you do with common data if you're sharding, right? So, but let's just put that down as inconsistencies between shards. Between shards. And my handwriting is terrible, so I'm sorry. Yes?
It might be hard later to add shard because you basically have to add a migration.
Excellent. Right. So that's a really good point. His point was rebalancing, or I like to use the word restructuring your shards. Right? Same thing. Okay, that's a good one. Okay, what else? And we've hit almost everything. There are a couple others maybe that we need to think of. Okay, this is good. So let's talk about this. And we're going to hit all these points real quick. All right, so where's my remote? All right. So this specific bullet here talks about what you just mentioned, which is what happens when a shard goes down. Okay, so this is both good and bad. All right, let's say the shard that's holding in our stupid example, let's simplify this and make it more complex at the same time. Let's say we do sharding for our user table based on their last name, and we'll do 26 shards, A, B, C, D, etc. Right? So shard P goes down, and now everyone whose last name is P, no longer their data is available until you bring it back up. Okay? So that's good and bad, because now the other 25 shards are continuing to operate. So our whole system hasn't gone down. It's just those people have gone down. Now the complexity there becomes twofold. How do you accommodate for that in your application? Right? So my last name starts with the P. What does your last name start with? M. Okay, so hers starts with M. So when I go to the website, my stuff will not pull up. but Ms. Mehta's information will come up. But how do I, as an app developer, like signal something in the application that says, oh, everyone with the last name of P, we need to show this page, right? It's not hard to do, but it's something that we now have to code and we have to manage, right? So what we've done is we've made a trade-off that we get all these shards, we'll get a overall higher level of uptime, but now we've introduced some complexity because now we have to accommodate for that, okay? So, yes, go ahead.
You can also, well, you can replicate, no?
We could do replication and all that kind of stuff. You're absolutely right. So the chance of a shard actually going down is actually very small, right? Typically, especially like even if you do active standby for that shard, right? If you do an in-region active standby, you can immediately flip to the other one. Okay, but again, this is this is not a hypothetical situation, but it is an edge case here. Okay, you're absolutely right. Okay, so there's that, and then. Why is there a blank slide here? That's weird. Okay. So, like you were saying, you can have replica sets within each, well, not like we were saying, but to improve the performance of a specific shard, you can have a replica set for that specific shard. So if we use the example that I was just talking to Ms. Mehta about, the M's will have a replica set inside of it, the P's will have a replica set inside of it. And what this allows you to do is it allows you to solve the inconsistencies, number one, unbalanced shards. Because I would probably guess that the number of people who have a last name starting with P is way, way higher than Z, right? So now you have to appropriately size your Z database as opposed to your P database. But we can solve that using a replica set, right? So we can say, okay, we know there's like 800x times more last names that start with P, whatever. Okay, right? So that's one way we can tackle that. But again, this is some complexity that now you have to think about. Okay, how do we deal with unbalanced shards? Are we putting too much compute resources or storage or database resources for Z, right? You can't have like the same database size for each of the shards in this case, right? So if you do like this manual sharding. Okay. And I don't want to get into logical and physical shards. We could talk about that, but it's fine. Well, one of the other key things is that we typically shard on quote unquote different machines, of course. And so far we've talked about what's called static sharding, right? That means we have A, B, C, D, and we just have some kind of in-memory map or whatever where we say shard A goes to this server, shard B goes to that server, et cetera, et cetera. So we've basically done what's called static sharding. What we could also do is we could also do dynamic sharding, which gives us a little bit more flexibility, but then it leads us to points number 1 and 4, like unbalanced sharding, and I'm sorry, number 5, which somebody mentioned, which is rebalancing your shards. Okay, so we do this routing based on key. We send DBs or we send the request to a specific database, et cetera, et cetera. And what does the sharding router look like? Right, so we have 2 examples here. If we do a static lookup table like this, we just say, okay, this is A through M's go to server 1 or shard 1, N through Z go to here, right? This is our static sharding strategy. And on the right here, we have something more akin to a dynamic sharding where we maybe have some code that says, okay, on this case, send it here, on this case, send it here. And we can simplify this by just using an API gateway, right? This diagram isn't actually 100% correct on the right, because what we would do is our API gateway wouldn't directly hit the shard. It would hit our application running that sits on top of that specific shard, right? And that application, that instance of the application is locked into shard 1, and there's another instance of the application that's locked into shard 2, et cetera, et cetera. Okay? But again, this adds a little bit of complexity, but it does give us the flexibility, right? So you mentioned like a rebalancing and restructuring of our shards, right? So what we can do in the thing on the right is we can say, oh, you know what? Our shard A or shard 1, it's getting quite big. So whenever we create a new user now, let's send the new users to shard 2. And then once that fills up, let's send it to shard 3 or whatever, right? But that's additional complexity we have to manage. And if we think of that is basically a kind of almost an upfront architecture design choice. Rather than trying to rebalance a shard once the data is in there, let's balance the data up front as we insert stuff into a shard, right? So that's an architectural decision that we're making, right? So, and that idea is not unique, right? If we think of, and I'm going to totally get this wrong, so you'll have to help me. What kind of data structure is it that when you insert something into the data structure, it's inserted in a sorted way? What's that called? I've forgotten. What's that? What's that?
Indexed.
No, not indexed. Right? There's just something, a very specific word in computer science algorithms, where like if you have a list, and when you put something into the list, you put it where it belongs. Yeah, it's basically like, no, you're right. Yeah, it's basically an ordered tree, right? That's right, or a sorted set, right? So that's essentially what we're doing, but not down at the code level. We're doing it at the systems level. Okay, so anyways. All right, so let's talk about some pros and cons with this. Yes, go ahead, please.
Much more complex to retrieve the data. If we compare it to the like rebalancing all the data and then upload it working with the new structure.
Right.
Maybe the example is much more near like a partitioning in Cassandra. It's not like moving the new data to the new one. It's just rebalancing all the data through the all the instances. So whether we'll do in a way that you have is it easier? Will it be harder to retrieve the data?
Okay, so so that's an excellent question, and that's something we didn't put up on here, which we should have. Let me just add it up here real quick, right? And which is number 6 is shared data. Okay, so we put all the data into shards, but now the question becomes, for data that's going to be in every shard, in every database, right? What do we do with that data? Do we just keep this database to the side and have all the quote unquote shared data here? And then we query this thing and we query our sharded data over here? Or do we replicate that data across all the shards? And if you pick option 2, which is okay, we have, let's stick with the example that we were talking about. Like we have users sharded A through Z in these databases, but the users also need to be, the other queries that we'll need to do is we'll also need to go and get all the data for the products and items that we have. Right, so it's no longer a single database. Actually, that's too simple of an example, but let's just roll with it for now. Right, so now do I query the orders database and also, or not orders, the items database, and we query the user database to get their order data, or do we just push all of the items into the shards? I don't know the answer to that, right? And it's not that much of a contrived example, to be honest with you, because that's when you start doing sharding, you have to think about this. What's the trade-off I'm making here? I make 2 queries, or do I make 1 query? Right? Or hit 1 database, right? And that becomes problematic, for example, when select user order, comma, items. I want to get all of the user's items and all of the data that for all the items that they have in their shopping basket, right? So I'm basically selecting and doing a select across 2 tables. Now that's easy to do in a single database. I just say, give me all the orders, or sorry, all the items in order for this user, and you just pull it out and boom, you're done. Or okay, now I need to go find that user's shopping basket, and then I need to go and query this other database after I have a list of all the items in that order. Now, how do you get a list of all the items that are in that specific order if you don't have the user's key in that orders database or that items database? Now what you have to do is, okay, I need to query the details for this t-shirt that they ordered. I need to get the details for the shoes that they ordered. So you're making multiple queries across your products database, possibly. Yeah, go ahead.
Hearing you in a way, it's like, I think the biggest problem in sharding is that you're taking internal mechanisms that usually a database does,
Yeah.
optimization, execution patterns, all
Yep.
the application level, which is you. Now you need to handle all of this.
Yeah.
This is the great example, actually.
Yeah.
You know, you need to handle the indexing. You need to handle, you're actually doing it manually.
Yeah, that's right.
And all the cluster of problems is that instead of letting some magic inside a database do that, you're doing that.
Yeah, that's right.
Hard. That's hard, obviously.
Yeah, absolutely. And like you were saying before, just use Redis to do sharding. It makes the life easy. I'm gonna have to play around with that. I haven't tried that before, but that looks pretty good. Okay, so let's just summarize this real quick. The pros of sharding, you get almost infinite scalability, which, I mean, you can't really say that about almost anything else that we talked about, infinite scalability. We get that specific level of fault tolerance, right? Because when a shard goes down, you don't lose everything, which is nice. You can also tune for better response times. What are some of the cons? As we talked about, added complexity. We talked about the non-uniformity of data across shards. The Zs will have 1 million rows, but the shard that contains Ps will have like 10 million rows or something like that. Okay, and we talked about certain queries can be more complex because now you need to join a shard with this other database over here. And this is a term that we commonly use when we talk about sharding, is now when you do those certain types of queries, what we've done in sharding is we've scattered all the data, and now we have to gather all the data. So how do you deal with that? What kind of code do you write? And like the gentleman said in the back, you're basically moving what the database does in terms of optimizations and other things like that. You're moving it up into the app tier, and guess who has to manage all that now? You do. So, okay. All right, so we have CQRS, and oh my God, I'm not sure how we're going to get through this in even 20 minutes, but let's start. Let's try, okay? How many people are familiar with CQRS? Okay, so fair number of folks, about half the room. How many people do CQRS? 2 people. Okay. What do you use as like some of the tech for your CQRS deployment? Like you're using Kafka for event sourcing, or do you use something else?
Actually, Kafka, the configuration part of what is done from my side.
What's that? I'm sorry, hold on. Let me turn this microphone on. I forgot this was here. Can we turn up this mic? Okay, here you go. I should have been using this the whole time. I'm sorry. Go ahead. Hold on.
From development side, we were using mainly the Kafka, but like all the configurations because we have an on-premise. Because of our projects are more governmental, is done from the DevOps side, from their side. So yeah, but for the like messaging, I will say more messaging for the CQRS, not the streaming. It was like Kafka.
It was what?
Kafka.
Kafka. Okay. You had your hand up too. Go ahead.
Yeah, same. In my case, we were using Kafka.
Okay.
And had like a separation of command topics and then event topics, and using a mix of CQRS,
Okay.
Event sourcing, domain-driven design.
Okay, got it. All right, so I'm going to come back to you two in a few minutes when we talk a little bit more detail about some of the nuances of this. Okay, so okay, we'll skip the hype part. We'll make this go a little faster. All right, so the base problem that CQR solves is on this slide. Data contention with locked records. Okay. So for those of you who raised your hand that, oh yeah, I know what CQRS is that correct or incorrect?
I'd say it's one of the benefits.
Okay. What are some of the other benefits then? Let's hear it.
I think it's a separation of concerns.
Separation of concerns. Okay. That's a high level code and architecture benefit. Sure. Yeah, I got it. Okay. What's that? Incremental data change. Being able to adapt to incremental data changes. Okay, that's a good one. Yeah. Yeah.
Replay your state.
You can do replays. Maybe. We'll talk about that in a second. Yes, if you're thinking of Kafka, yes. Okay. Anybody else? Okay. All right. So, what does this look like from a diagram point of view? Right. So you have your API up here at the top. You send commands into some kind of queue. Those commands are executed by some kind of code, or it's the code that you write, that updates the database, i.e. does a write. That may go into a cache, a replica set, or a materialized view, and then your API queries that thing on the write. So essentially what you're doing is you're separating the write portion of your application as in WRITE, the write code of your application from the read portion of it, okay? And I was a little surprised that more people don't do CQRS in here, but that's okay. All right, if we look at this in a slightly different way, one of the complexities that you hit on or you come up on almost immediately is on this slide, okay? Sorry?
Consistency.
Yes. Well, not just consistency of the data, but consistency of.
State.
Yeah, it's on this. It's on the diagram, in the middle of the box, right? The model. Right. So now that you've separated this out into a write portion and a read portion, is your model going to be the same for both these applications? Are you sure? Is that a good idea?
But now we're writing in the database.
Hold on. Let me give you this so everyone can hear you. Okay, go ahead.
So wherever like we were writing in a database, we were just writing the change increments. So like the data structure is really very different from the reading database, where all the object is stored. So the models are really different for the read and write.
Okay. So your position is that the models are very different for the read and write portion.
The one is like audit change, and another one is
Yeah, no, I don't think that's incorrect. I don't think that's incorrect, but yeah, go ahead.
In my mind, it's like Materialized View.
Okay, it's like a materialized view. Okay.
So you have truth, it's like a right portion, and the read.
Sorry, let me just give you this, so you don't have to talk.
So it's my in my mind, it's like you have the right portion, which is the truth,
Right.
and the read portion, which is kind of Materialized View.
Okay. Right.
So you can replay it maybe and recalculate this portion, etc., etc.
Right. Okay. But the model is different.
Not exactly, because it's actually a reflection of a model.
Okay.
So
It's not completely different. It's a little different.
Yeah,
That's what it
yeah,
sounds like you're
yeah.
saying. Okay. You don't need a microphone. You're loud. Go ahead. Just joking. The model is what?
Derived,
The model is derived for which part?
because you have series of commands
Right.
updating all the time.
Right.
And when you come to read, it's always the calculation and the computation. It's like it's event source.
Right.
The derived state. of
Derived state.
all
Okay.
the series of commands.
Right.
So I think it's a derived model.
Okay. No, I think that's perfectly valid. The thing is all three of the responses are actually perfectly valid, right? So there's not like a recipe or cookie cutter way of doing this. But I think the point I'm trying to make here is that we have a model here that represents the command. We have a model that represents the data that you're reading, i.e. the derived data. But now you're maintaining two different models, which is not necessarily a problem. But I like to think about this up front, because if I'm maintaining two different models, what happens if I make a change to the command model? Do I need to now go and change the query side of the model to reflect that new change or new data I've added? And what's the friction in doing that? Right? Again, I'm not saying it's wrong or it's bad. It's just now I have something else I need to worry about, whether I'm the architect or I'm the developer. Right? So of course, again, everything is a series of trade-offs. All right, so let's look at one more diagram really quickly. And this is, so the two folks who responded that we do CQRS with query, you probably can look at this diagram and say, yep, this is what we do, right? So instead of the kind of high-level boxes we have our command app. It does a write to a Kafka log, and we also have a Kafka processor. Here's our event source, Kafka topic. We have a stream processor that updates the database, and that goes into blah, blah, blah. Okay, right? So this is a little simplified, but this pretty much defines it. We could put in transformations and different kinds of processors over here on the right side. And if you go to the Confluent website, they have all this detailed, and you guys have probably read that. I think most of you actually, most of you raised your hand. So you're familiar with this overall topology. Yeah.
I have a question. If this architecture is a good fit if you have many writes, so could it be that you have it will be the latency will get bigger when you have many writes? Or
Okay. So the question is this architecture good when you have a lot of writes? Will there be a lot of latency if you have many writes? So if you remember, I think the second or third slide, Be careful. I started with here. Oops, I gone too far. Let me go back. Let me flip forward. When I think about CQRS, the main thing that comes to mind for me is this part right here. Okay? So CQRS, like from a, let's say, operational point of view, it solves this specific problem very well. And so I think that answers your question. The answer is yes. If you have lots and lots of rights, CQRS, okay, and you're gonna say something completely different, which is great. So, okay, here, let me give you this. Okay, only I can say that.
So, is it working?
Yeah.
Okay. So I think the answer depends. Like, are these like rights related to the same, let's say, ID? If they are, then this architecture is no good because Kafka streams will process them in order. And also, it depends if you need low latency, because again, Kafka doesn't work very well with low latency, but it works very well with big number of transactions and messages. So the answer is it depends.
Right. No, that's a good answer. So the other question, and you actually hit one of the keywords that I was going to bring up, transactions. Right? How do you ensure ACID transaction capability in this kind of architecture?
Again, eventual consistency, that's the matter.
Right. But again, like he was saying, it depends, but we still want everything to be ACID, whether we do eventual consistency or we don't.
It's not acid. That's the problem.
What's that?
It's not acid.
Okay, why is it not ACID?
Because of the eventual consistency. Because eventually,
Okay.
like the way I imagine it, like you're doing an HTTP request response, you get an immediate response.
Okay, I see what you mean.
Here, you're waiting for every line, all of
Yeah,
this
yeah,
line
okay.
to be updated.
Yeah.
What happens if I'm doing a request right now, but someone already inserted the order?
Right.
I want to know what my order is. That's the problem.
Right. Okay. No, you're right. Eventual consistency is not. It's not 100% acid, but it's eventually acid. I'm just joking. That's right. Yeah. Good.
Actually, I might.
Is it on? Here. Did I flip it off? Maybe I did. Okay.
Actually, if I can step in a little bit, it can be made ACID if the commands also go in a topic, and then we use Kafka streams and Kafka transactions.
Oh, interesting. Okay.
I mean, when you say Kafka transaction, it's the way Kafka works, that it says begin and then end as a message, right? If I remember right.
Yes.
It still takes time. But again, it still takes time to update.
Well, with Kafka streams, you have a way of doing some sort of like sharding, where different partitions get assigned always to the same process, so that
Right.
if you somehow match.
So you can actually write and wait till it will be read by consumer?
Yes, yes, and make sure that you're the only process that processes that partition, and so then you also have consistency. You have transactions of messages that you consume from the command topic with the messages that you publish.
But then why we need to make it at all?
Right. So let's table that discussion for the time being, because what I'd like to do is talk about doing this without using Kafka, right? Kafka is like all the high rage right now. You know, everyone's talking about everyone thinks that they're doing it or wants to do it, whatever. But like if we just go back to this slightly simplified model, why not just use a message queue for the command part instead of using Kafka? Like ActiveMQ or whatever is in your cloud. What's that?
Because retaining is important. The
Why?
retaining of the data.
Why?
Because you would like to be able to restore the state to replay and restore the state in every time.
Okay.
If something happens,
Okay.
it falls, you want to restore the
Okay.
data that you're querying the data on. You have to be
I got you.
calculated.
I got you. And I'm not disagreeing with what you're saying. However, I'm saying if you don't need that replay capability, or let me rephrase that. Let's say we just use standard JMS, okay? We get transactability on everything, right, that we put into it. And yes, there's going to be a little bit of a lag time there, right? But we can program our command processor to, look for different things and, whatever. We can accommodate. We have a lot more edge cases that we can accommodate for when we use a transacted Java message, or JMS, basically, right? It's transacted from start to finish. We don't need to use Kafka. When the command processor finishes, it stores the record of truth in the database or wherever you're saving it. Right? You see what I'm getting at now? It's like there's, and again, I don't have anything against Kafka, but I'm a programmer too. Whenever there's a shiny new object, I'm like, ooh, let's use that. That's great. It looks like so much fun to learn that. But for something like CQRS, if you need like that strong ACID type of thing, why not just use a message queue? You don't.
Microservices, why doing it all together? What do you get?
Okay.
Then why doing it all together? Just
Yeah.
more complicated.
No, I got you. Hold on. Let me get to the next slide. I'll come. I agree with you. There is some complexity here, but right. It's about it's about working in a scenario where you have a high number of writes, right? And you want to do it at scale. You're doing data management at scale. You have a large number of writes. You also have a huge number of reads. How do you accommodate for those large number of writes into a data store while still having read support? Because the classic problem with the database is that once you start doing lots of writes to a database, what does it do? What's the trade-off you're making in just a standard SQL database? What happens? You're doing a large number of writes. Well, space is an issue, but right, the locks. And what do the locks cause a problem with? Okay, there's contention, which leads to your reads being way, way too slow.
But you had a simple solution for that. Optimistic one.
You do what?
Optimistic one.
Optimistic locking. Are you sure? Okay. So when I was at AT&T, we did optimistic locking, right? And because we had like literally thousands upon thousands of change orders coming in or creates or whatever into the system, with optimistic locking, what would happen is two things come in to manipulate the same order, right? Order object in an Oracle RAC database server. Optimistic locking was used initially. Oh no, this was changed while the two transactions were running, so you do a rollback. And a rollback in a database is extremely expensive, right? It's even more expensive than locking. So yeah, optimistic locking sounds like great on the surface, but now you put a huge amount of load on the database too, right?
But optimistic locking works well in case that chance of doing of this what you explained is
Yeah.
low. So you have a very low number of very low ratio of these cases, so overall you have benefit.
Okay. Again, it depends answer, right? And I'm not going to disagree with that. The issue with optimistic locking is that when you have a large number of writes, there's a tipping point where now all of a sudden you're getting so many writes, and there's the probability of having to roll back the optimistic lock gets higher. So up until a certain point, yes, you're going to do great. But once you reach that tipping point in your application, when you get a massive surge of whatever changes, mostly changes for optimistic locks, that's when you have problems. Yeah, no. I'm not disagreeing with you. It's just how it's the large number of writes that becomes a problem. So, anyways, let's try to round this out really quickly. Wait, am I in the right one? Okay, yeah. So, I would consider using queues instead of Kafka to do this. Right? Again, it's use case dependent, but you get a little bit more of a rigid environment. If you don't care about replay especially, it's fine. Your database or your data store is where you record everything, or is the truth for your data. And then, right, we talked about consistency and eventual consistency issues. In terms of application design, we write to a model, we read aggregated data, we can put indices on the reads, right? And one of the problems here is that when you have a lot of indices, and this is why this CQRS separation thing is good, when you have a large number of indexes on a table, what does it cause? What's the side effect of that? The write is much, much slower now because every index that you add is an extra operation that has to be updated every time you write to a row to that table. Okay, so it helps solve that problem also. Right? So consider separate model for read and write, which we already talked about. Have a completely separate app for read and writes. Okay. And finally, why do we even need a query DB? Do we need a query database? We have the write database, but I'm not going to get into that. Right, but like, and I know this is Kafka again, but what I'm trying to get at is, right, so we have our writes going in here. Instead of updating a database, why don't we just put everything into some kind of cache or into Redis or whatever? So yeah, so you still have your database, right? That has all the stuff in it, but when you write to the database, you also write to the cache. And the reason for doing that is in case your Redis goes down, well, you have the database and you can repopulate the, you have your SQL database or data store or whatever. You can repopulate your Redis cache if you need to. So you can actually just get rid of the query database altogether. Okay, you just use the cache, right? And I'm sorry, we didn't get a chance to talk about Ignite, right? But you could also use like Apache Ignite. We talked about Redis quite a bit, Memcached, etc. Right? And I don't really want to go into this. This kind of makes sense, right? When you think of breaking up the model into a read and write, on the left side here, your command is create shipment command, blah, 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 update shipment, and on your right side, items by order ID query. So you can kind of separate out your model into two different parts too, but then you have to remember to update one or the other whenever you make changes to it, right? Just have to be aware of that, something else conceptually. All right, so we have 7 minutes left, and I don't want to go into this compensating transaction pattern in too much detail, but I think most people are familiar with this from an architectural level, which is that this thing is, let me get to the punchline, right? Transactions, we've been talking a lot about transactions, right? So the idea here is that with a compensating transaction pattern, say that you have multiple operations and op1 works, great, op2 fails, then what you have to do is you do a compensating transaction which rolls back operation 1. Okay, so it's a way of not doing distributed transactions. Has anyone worked with distributed transactions in the past? Right, so one lucky person, right? One of the systems I built many years ago used a distributed TX across a JMS and a database. And it didn't scale, unsurprisingly, right? It's slow. But that's what we ended up doing is basically building a rollback or a compensating transaction and getting rid of the distributed transaction so we could scale it up more, right? It put more pressure on the database in one sense, but it took a lot of pressure off because we weren't locking rows or tables in the database anymore. Okay? So if we want to think of this in a slightly different way, oops, sorry about that. Right, so a typical scenario is you need to book a user a trip. They need a car, they need a hotel, and they need a flight. The car got booked, the hotel got booked, and boom, the airfare changed on the flight in the few minutes. Nowadays airlines do like almost real-time like fare calculations, which is very annoying. So like the best time to buy tickets is like Tuesday morning, or I don't know. There's an article on it. You can go read it. Okay. Anyways. So this fails. So now what we do is we undo this transaction for the hotel booking. We undo this transaction for the car booking. And we return to the user unable to book your trip, right? So kind of standard compensating transaction type of things. When we do two-phase commits, we lock multiple transactions or multiple resources like I was talking about with distributed transactions, slow because of coordination, locking issues, minimize clients, complexity of design. And I just want to finish this specific part on, yeah, someone was talking about this earlier. Unfortunately, we don't have time to go into the Saga pattern. But there's actually a lower level pattern called the Saga pattern, which you can use to do compensating transactions. And you don't have to write all the code for this, thankfully, because you can just use Apache Camel to do this stuff, believe it or not. Okay, see if I have an example of this somewhere. Yeah, this is similar. Here it is. All right. So is everyone familiar, or at least knows what Apache Camel is? It's an enterprise integration library, right? So what you can do with Apache Camel is you can actually program sagas. So you can say, okay, go and do this. run this bit of code, reserve credit. If it fails, here's the compensation. Direct invocation of the refund credit class, and you can kind of see how that works, right? So this is basically goes and runs this thing and then runs this other stuff here. Okay, so anyways, we don't have time to get into this but in too much detail, but Apache Camel provides a very nice way of building out sagas or doing compensating transactions so that you don't have to write all of the low-level mechanical code to make it happen. What you do have to write is you have to write the extra code to compensate for the transaction, but you don't have to wire everything together and manage it at a low level. All right, so very quickly, we've been talking about data management in the cloud, right? So what I want to finish on, this will only take a few minutes, right? I can breeze through most of this. What I want to talk about is, as a developer, I love building challenging, cool stuff and using all the latest cool tech, right? Who doesn't? But there are certain times which is like, maybe I should just use something off the shelf. So these are a couple of off the shelf things I think you might be interested in, okay? So, right, why do we need to reinvent the wheel? As you know, most of the really interesting big data tools, frameworks, whatever, are typically at Apache, right? Which most of you, Apache Kafka, for example. We're not going to talk about Kafka. Everyone's probably familiar with it. But I want to talk about these last two a little bit. I like the one in the middle a lot, actually. So Apache Pinot is a real-time distributed online query platform. So what it does is, so when you go to LinkedIn, for example, and updates come in through the web browser, they're actually using Apache Pinot underneath the hood. So instead of building out like this online analytical processing engine that's fully distributed and sharded and blah, 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 you can just basically roll this. And it takes a little while to learn it, and you have to write some code for it, et cetera, et cetera. But this is a emerging product, and it's open source, of course, that's really interesting. Okay, so it's worth having a look at this, and it does lots of things underneath the hood so that you don't have to manage it. You basically just shove data into it, you write some code, you write some queries, et cetera. So LinkedIn use it for sending notifications, and Uber Eats also use it for doing like updates to restaurants, for example. Okay. So, right, near real-time ingestion of data from Kafka or from anything else, low latency queries. The queries look kind of like SQL. Okay, so it's a fun product, and I think there's someone from there's a company behind the open source product called Startree. I think someone from Startree is here, so at the conference at least. All right, so LinkedIn used by profile. It's used for anomaly detection in certain like bank fraud types of things. Again, it's worth checking out because I like it when I don't have to work all weekend to build something very complex, right? It's nice to just pull something off the shelf if you can, right? So batch and stream type of thing. Oh, sorry. So let's talk about Beam for a minute. Does anyone use Beam before? Okay, so a few folks. How would you describe Apache Beam? Oh, you raised your hand, sir, right? Yeah. Okay, how would you describe Apache Beam? Okay, perfect. So Apache Beam is really cool. It lets you do things like ETL, and like gentleman said there, batch processing and different types of stream processing. And you can see on the left here, even though it's written in Java, it is written in Java, isn't it? Apache Beam? Right, there's an implementation for each language, right? So we have Python, Java, and you basically write models and you do the steam. There are different types of runners that you can also inject. Or, sorry? Did Beam come out of Spotify? I don't remember. Maybe it did. I don't know. Right. So I've used this for a couple projects, specifically on. Well, this is kind of what it looks like. You write these classes where what this is doing is it's reading an input file, it's doing a flat map, lowercasing everything, et cetera, right? So you can kind of get an idea of how you write code for Apache Beam. But where I've used this is on Google Cloud. Now I'm going to totally get the name wrong. What's it called on Google Cloud? Dataflow. Thank you. Right? All these words are so similar, right? So Airflow builds on top of Beam, and Google Cloud has a implementation of it running called Dataflow, which is kind of nice. Okay. So there we are. It looks like we finished just a little bit late. Is there another session after this, or is there anything else after this? Or what time does the next session start? I don't want to. Oh, at 5 o'clock. Okay, good. So I can continue rambling for another 20 minutes. I'm just joking. So, all right. So, anyways, thank you for coming. If you enjoyed the session, please go to the app or whatever, give it 5 stars. If you didn't like the session, please email me or text me or talk to me. I'd love to get your feedback if you thought like, oh, maybe you could do this better, or maybe talk more about that. Okay. So I appreciate all of you coming, and I'll let you all go so you can take a break before the next session. But I'm happy to talk with folks. Oh, and also come by the booth to get this Zool booth to get this cool T-shirt, and you can be the cool person in your office with this swanky Java virtual machine hat. Okay, so come by and say hello. Thank you.